66 million years ago, life on Earth did not simply disappear when an asteroid struck. The first day was only the beginning. Forests burned, coastlines were overwhelmed, dust and debris entered the atmosphere, and ecosystems that had endured for millions of years were pushed toward a crisis they could not easily escape. Roughly 3/4 of Earth's species would eventually vanish, while a few surviving lineages inherited a radically changed world. So what really happened during the extinction event that killed about 75% of Earth's species, and how much of that catastrophe truly began within the first 24 hours? 66 million years ago, Earth was an ancient world, filled with ecosystems that had been changing for far longer than any human history could record. The continents were not arranged as they are today, but were moving toward familiar positions. Sea levels were higher than in the modern world, and shallow seas covered areas that are now dry land. The climate was warmer, with little or no permanent ice at the poles, and forests extended into regions that would later become much colder. This was not a primitive planet waiting for something important to happen. It was a biological world, crowded with species shaped by millions of years of evolution. Flowering plants had spread widely, insects occupied roles, and rivers, wetlands, forests, coastlines, and open seas supported communities of life. Dinosaurs were the most conspicuous animals on land, but they were only one visible layer of a much larger system. Birds were present. Mammals lived in many forms, most of them small compared with the largest dinosaurs. Turtles, crocodilian relatives, lizards, amphibians, fish, ammonites, plankton, and other organisms filled environments from freshwater streams to the open ocean. Every habitat depended on exchanges of energy that began with sunlight and photosynthesis. Plants on land captured solar energy and became food for herbivores. Those animals, in turn, supported predators and scavengers. In the seas, microscopic organisms near the surface formed the foundation of food webs that extended upward through fish and other predators. The stability of this world did not mean that nothing changed. Climate fluctuated. Volcanoes erupted. Species appeared and disappeared. Populations expanded or retreated when conditions shifted. Evolution never stopped. Yet most organisms were adapted to disturbances that unfolded within ranges their ancestors had already encountered. A drought might favor one species over another. A volcanic episode could transform a region. A changing shoreline could destroy one habitat while creating another. Life survived because change was distributed across space and time. That difference matters when we think about the distant beginning of the human story. Our own lineage did not yet exist, and no primate resembling a human walked this landscape. Still, the biological ancestry that would eventually lead toward us was already embedded among the small mammals living beneath the ecological dominance of dinosaurs. Those animals were not waiting to become human, and evolution had no destination. They were simply surviving generation after generation under conditions suited to that age. Forest communities regenerated after fires and storms. Rivers changed course, but continued to carry water. Seasons returned. Animals migrated, nested, hunted, fed, and reproduced according to inherited patterns. Fossils show that late Cretaceous ecosystems could be highly diverse, although their exact composition differed greatly from place to place. North America was not the same as Asia. Coastal environments were not the same as inland forests. Tropical seas were not the same as higher latitudes. There was no single Cretaceous landscape, just as there is no single landscape on Earth today. This complexity matters because the catastrophe to come would not strike an empty stage. It would strike millions of relationships at once. A leaf eaten by an insect, a seed carried from a parent plant, a small mammal sheltering underground, a plankton cell near the ocean surface, and a dinosaur feeding across a floodplain all belonged to different scales of the same planetary system. Their survival depended not only on their own bodies, but also on the continuation of the environments around them. For millions of years, those environments had changed without collapsing everywhere at the same moment. Then, near the end of the Cretaceous, that long pattern of ordinary change approached a boundary unlike the disturbances most living species had evolved to endure. What happened next can only be understood by first seeing how much life was already there, how deeply connected it had become, and how much evolutionary history was about to be placed at risk forever. When people imagine the last days of the Cretaceous, the first images are usually enormous dinosaurs moving through forests, floodplains, and coastal lowlands. They deserve attention, but they can hide the larger truth of that world. Dinosaurs were only one group inside a living system that depended on countless smaller organisms. Beneath their feet, insects moved through soil and leaf litter. Flowering plants spread across many environments, while conifers, ferns, and other vegetation shaped forests and open ground. Rivers carried fish, turtles, amphibians, and crocodilian relatives through freshwater habitats. Along coastlines and in shallow seas, mollusks, crustaceans, fish, marine reptiles, and microscopic plankton formed complex food webs. The survival of a giant herbivore depended on plants, but those plants depended on soil, water, fungi, insects, climate, and seasonal cycles. Predators depended on prey, scavengers depended on death, and decomposers returned nutrients to the ground. What looked like a world ruled by dinosaurs was actually a web of dependence. Mammals were present as well. Fossils show that late Cretaceous mammals occupied different ecological roles. Some climbed, some dug, some probably fed on insects, seeds, or other small foods, and their body sizes were generally modest compared with the largest animals around them. None of these creatures was moving toward humanity as if evolution had a plan. The distant lineages that would eventually contribute to the ancestry of primates were simply surviving under conditions that favored their own forms of life. That is a quiet connection between this ancient world and our own origin. Human beings were still tens of millions of years away, but the continuity of mammalian life across the coming crisis would later matter to everything that followed. Birds also lived in this world, including ancient groups that later disappeared and lineages related to those that survived. Their presence reminds us that the boundary between the age of dinosaurs and the age that followed was not as simple as one group vanishing and another taking its place. Birds are living dinosaurs, descendants of theropod ancestors, and their survival would carry one branch of dinosaur evolution beyond the catastrophe. The oceans reveal an important story. Microscopic plankton near the surface captured energy or fed on organisms that did, supporting larger animals above them in the food chain. Ammonites were widespread marine animals, and many kinds of fish and reptiles occupied different levels of the ocean ecosystem. These communities were linked to chemistry, temperature, light, and nutrient circulation. A disruption at the base of the food web could spread upward, even when larger animals survived the first physical disturbance. That principle would become central later, but before the impact, it was simply how the biosphere worked. Life was connected through dependencies that were often invisible. A large animal could appear powerful while relying on fragile processes occurring in leaves, soil, water, and microscopic cells. The same is true of human life today. Our bodies and societies seem far removed from those Cretaceous ecosystems, yet we still depend on photosynthesis, stable food webs, functioning oceans, and the transfer of energy through living communities. The deeper origin of humanity belongs inside that continuity, not outside it. We emerged much later from a planet already shaped by environmental change and survival. To understand what was lost near the close of the Cretaceous, we have to look beyond the famous animals. The coming extinction would erase entire branches of evolutionary history, including organisms that left no descendants. Others would pass through the boundary and become the ancestors of later ecosystems. The difference between disappearance and survival would not always depend on strength, size, or dominance. In a crisis, large enough to alter the basic conditions of life, the fate of a species could depend on where it lived, what it ate, how quickly it reproduced, and whether the resources it needed remained available after the world around it began to change. For millions of years before the end of the Cretaceous, life on Earth had endured change without experiencing the kind of global disruption that was approaching. Continents shifted slowly. Seas advanced and retreated, volcanic activity altered landscapes. Climate changed over long spans of time, and species responded by moving, adapting, declining, or being replaced by others. From the perspective of any single organism, these changes could be severe, but many unfolded gradually enough for ecosystems to reorganize. Plants could spread into new areas. Animal populations could move along coastlines, river valleys, and forests. New generations could inherit traits that worked slightly better under changing conditions. The living world was never truly stable, but it was accustomed to change that usually arrived through processes operating over years, centuries, or much longer periods. That distinction is important because adaptation is not preparation in the conscious sense. No species can anticipate a catastrophe. Evolution does not look ahead. It works only through differences in survival and reproduction under conditions that already exist. A dinosaur adapted to a particular food source was successful while that food source remained available. A marine animal adapted to a certain temperature range could thrive while ocean conditions stayed within that range. A small mammal able to hide underground did not evolve that behavior because an asteroid might one day strike Earth. It simply lived in ways that had been useful in the environments of its ancestors. This is one reason dominance can be misleading when we look backward through deep time. Large dinosaurs had occupied major ecological roles for an extraordinarily long period, but long success did not make them immune to rapid environmental change. The same was true for many organisms in the oceans. Entire lineages had persisted through countless generations, yet persistence depended on the continuation of basic ecological conditions: usable habitat, food, water, light, temperature ranges, and reproductive success. If several of those supports failed together, past success offered little protection. The future human lineage was still remote, but the principle reaches directly into our own evolutionary beginning. The small mammals alive at the end of the Cretaceous were not more advanced than the larger animals around them. They simply possessed combinations of traits that in some cases would later prove compatible with survival under radically altered conditions. Their descendants would eventually diversify into new forms, and much later some branches would give rise to primates. Nothing about that outcome was guaranteed. If the coming disturbance had unfolded differently, the biological history leading toward humans might also have taken a different path. The Cretaceous world therefore presents a useful contrast between ecological success and evolutionary security. A species can be widespread and abundant yet still depend on a narrow chain of environmental relationships. A forest can appear permanent while relying on repeated cycles of sunlight, rainfall, soil renewal, pollination, and seed production. An ocean ecosystem can contain enormous predators while depending ultimately on microscopic organisms near the surface. Strength at the top does not remove dependence on processes at the bottom. Before the impact, those processes continued across the planet with regional variations. Day followed night. Seasons returned. Photosynthesis converted sunlight into chemical energy. Plants grew. Animals fed. Predators hunted. Bodies decomposed. And nutrients returned to soil and water. The remarkable thing was not that this world was perfectly balanced. It was that its many disturbances normally occurred at different times and in different places. A flood in one region did not darken the sky over the entire planet. A fire in one forest did not simultaneously weaken marine food webs thousands of kilometers away. Local damage could be followed by migration, regrowth, and recolonization. The biosphere had room to absorb many shocks because they were distributed through space and time. Near the end of the Cretaceous, that pattern was about to change. A single event would compress destruction into a much shorter interval and connect environments that had previously been separated by distance. The danger was not only the violence near the place of impact, it was the possibility that several foundations of life could be disturbed at once, from the atmosphere above the continents to the food webs of the oceans. The organisms living then could not prepare for that possibility because natural selection had no knowledge of the future. They lived according to the conditions that had made survival possible until that moment. In this sense, the world before the catastrophe was not weak. It was simply adapted to a planet in which most changes arrived through familiar physical and biological processes. The coming crisis would test life under conditions that many species had never encountered, and the difference between surviving and disappearing would begin with how rapidly the environment moved beyond the limits their bodies and ecosystems could tolerate. Against the scale of Earth, the object that struck near the end of the Cretaceous was remarkably small. Most scientific estimates place the Chicxulub impactor at roughly 10 kilometers across, though its exact size cannot be known with complete precision. Earth itself is more than 1,000 times wider. Seen beside the planet, the asteroid would have looked almost insignificant, a tiny piece of rock moving through an enormous gravitational system. Yet size alone does not determine the consequences of an impact. What mattered was that this object arrived at extremely high speed and released an extraordinary amount of energy when it struck the surface. The contrast is difficult to hold in the mind. A body small enough to disappear against the curve of the planet could still disturb the atmosphere, oceans, forests, and food webs on a global scale. That is one of the central paradoxes of the extinction event. The threat did not come from something comparable in size to Earth. It came from something tiny relative to the world it changed. The impact occurred in the region of what is now the Yucatan Peninsula in Mexico, where a large crater lies buried beneath younger sediments. Evidence gathered from the crater, surrounding rocks, and the global geological layer associated with the end of the Cretaceous has allowed researchers to reconstruct the event with increasing confidence. The impactor did not need to destroy the planet physically. Earth remained intact. Continents did not break apart. The oceans did not disappear. The danger came from the way the energy of the collision was transferred into rock, water, atmosphere, and heat. Material near the impact site was shattered, melted, vaporized, or thrown upward. Shock waves spread through the surrounding region. Vast quantities of debris entered the atmosphere. Some material traveled far beyond the immediate area before returning toward the surface. The small object became dangerous because it transformed its motion into environmental change. This distinction is important when we connect the event to the much later origin of human beings. The distant mammalian lineages that eventually led toward primates were not saved because Earth avoided destruction. They survived on a planet whose basic structure remained, but whose ecological conditions were profoundly altered. If the asteroid had simply carved a local crater and stopped there, the evolutionary history that followed might have been very different. Instead, its effects reached far beyond the point of contact, influencing environments where animals had never seen the impact and could not have understood its cause. This is why the size of the crater alone cannot explain the extinction. The central question is how energy moved from one location into the entire Earth system. The composition of the rocks at the impact site appears to have mattered as well. The target region contained materials capable of releasing gases and fine particles when violently heated and disrupted. Researchers continue to refine models of exactly how much material entered the atmosphere and how long different effects lasted, so the details should not be treated as perfectly settled. The broader conclusion, however, is strongly supported. The impact injected enough dust, aerosols, and debris into the atmosphere to contribute to severe changes in sunlight and climate. A small extraterrestrial body, therefore, interacted with a particular geological setting to produce consequences far larger than its physical dimensions might suggest. Nothing about this required the asteroid to be enormous by planetary standards. It only required enough mass, enough velocity, and a collision with Earth. The idea helps explain why the first 24 hours matter, without falsely claiming that every later extinction happened inside a single day. The object itself arrived quickly. The transfer of energy began almost instantly. The environmental consequences then spread through different systems at different speeds. Some organisms near the impact region faced destruction within minutes or hours. Others lived far away and survived the initial day, only to encounter darker skies, damaged vegetation, falling temperatures, disrupted food chains, and changing ocean conditions later. The asteroid was therefore less like a giant object crushing Earth and more like a trigger that forced many planetary systems away from the conditions under which life had been operating. Its importance came from consequence, not visual scale, long before humans appeared. A relatively small body from space changed which evolutionary branches continued and which ended. The planet remained almost the same size, traveled along the same orbit, and continued turning beneath the sun. Yet the biological future moving across its surface had begun to change. The destructive power of the Chicxulub impactor did not come from size alone. Its speed was equally important because the energy carried by a moving object rises very rapidly as velocity increases. An asteroid only several kilometers across can become extraordinarily destructive if it reaches Earth at many kilometers per second. By the time the Chicxulub body entered the final stage of its approach, gravity and its original orbital motion had combined to give it an enormous amount of kinetic energy. When it struck, that motion had nowhere to continue in the ordinary sense. Instead, the energy was transferred into the surface, the atmosphere, and the surrounding rock and water. The result was not comparable to a large stone simply falling onto the ground. At such extreme velocity, the collision produced pressures and temperatures capable of transforming solid material almost instantly. Rock fractured, melted, and in some places vaporized. Shock waves moved through the crust. Material was accelerated outward and upward at enormous speed. The importance of velocity explains why comparing the asteroid only with the size of Earth can be misleading. A small object moving slowly would have produced a very different event. What made Chicxulub catastrophic was the combination of mass and speed, together with the geological nature of the place where it struck. Scientists estimate impact velocity using orbital physics, crater dimensions, simulations, and the properties of shocked rocks, but the exact value cannot be reconstructed with absolute certainty. For that reason, it is more accurate to speak of a very high impact speed than to treat one precise number as unquestionable. The physical principle itself is clear. Faster motion means much more energy available to be released during collision. That energy was concentrated into an interval so brief that the local environment had essentially no time to respond gradually. This difference between gradual stress and sudden energy release reaches directly into the long evolutionary history that eventually led to humans. Mammals had already survived many environmental changes before the end of the Cretaceous, but those earlier pressures usually unfolded through climates, habitats, competition, disease. or volcanic activity over periods that allowed some populations to shift or reproduce under changing conditions. A high-speed impact compressed an enormous physical disturbance into moments. Natural selection could not create new adaptations during those moments. Whatever traits organisms already possessed would determine how they experienced the consequences that followed. The collision also illustrates why the phrase impact event can hide several different processes. The initial contact lasted only a short time, but the energy released there immediately began producing other effects. The ground transmitted seismic waves. The atmosphere received heated gases, dust, and ejecta. Water near the impact region was displaced. Material launched upward could travel great distances before returning. Each process operated on its own timescale, and each carried part of the initial energy into a different environment. This is how a single point on Earth could become connected to distant ecosystems. The asteroid did not physically touch forests on other continents or plankton in distant oceans. The consequences reached those organisms through the systems that linked the planet together. Atmosphere, climate, sunlight, oceans, and food webs became pathways through which the original collision could continue to matter. The speed of the impactor therefore changed not only the violence of the crater-forming event but the scale of what followed. More energy meant more material disturbed, more intense heating near the impact site, and a greater capacity to alter atmospheric conditions. Yet even here, caution is necessary. Not every detail of the first minutes can be reconstructed perfectly, and scientific models continue to improve as new geological evidence is studied. What is strongly supported is the overall sequence. A high-velocity extraterrestrial body struck the region now associated with the Chicxulub crater, released immense energy, and initiated environmental changes linked closely to the mass extinction at the Cretaceous-Paleogene boundary. The event did not need to destroy every organism directly. In fact, many living things far from the crater would have survived the first moments without any physical contact with the impact itself. The more consequential question was, what happened after the energy moved beyond the crater? For the distant mammalian ancestors that would eventually contribute to our own lineage, survival would depend less on understanding the cause and more on whether they could endure the altered world that followed. The impactor's speed had turned a brief collision into a planetary disturbance, and the next stage would begin in the final moments before contact, when an ordinary piece of space rock was about to become one of the most consequential objects in the history of life on Earth. In the final minutes before the Chicxulub impact, nothing on Earth would have appeared to announce the scale of what was about to happen. The planet continued turning beneath the Sunday forests, exchanged gases with the atmosphere. Rivers moved toward the sea. Animals fed, rested, traveled, or remained hidden according to patterns that had existed for countless generations. Far above them, an asteroid was approaching at a speed no living organism could perceive or understand. There is no evidence that animals recognized what was coming, and it would be misleading to imagine panic spreading across the world before contact. The meaningful story lies instead in the physics. An object traveling through space at many kilometers per second was closing the final distance toward Earth, carrying with it an enormous amount of kinetic energy. In the last moments, Earth's gravity continued to influence its motion, but the impactor was already moving so quickly that the remaining journey would have passed in only a short interval. Atmospheric entry would not have slowed an object of this scale enough to prevent collision. Smaller meteoroids can lose substantial energy in the atmosphere, fragment, or burn away, but a body several kilometers across has enough mass to retain devastating momentum. As it descended, the atmosphere in front of it would have been compressed and heated intensely. Yet even this dramatic heating was not the main source of the catastrophe. The decisive transformation came when the moving body struck the surface and converted its motion into shock, heat, excavation, and ejecta. Before that instant, however, the world below remained biologically ordinary. This contrast helps explain why the event is so important to the distant history of human origins. The mammalian lineages alive then possessed no warning system for an event arriving from space. Their survival would depend entirely on traits that had evolved for other reasons. Small body size in some species, flexible feeding in others, sheltering behavior, reproductive strategies, and access to habitats that might remain usable after the initial destruction. None of these traits existed because an asteroid was expected. Evolution cannot prepare organisms for a specific future event. It can only preserve characteristics that have worked under previous conditions. The final minutes before impact therefore represented an unusual boundary between two kinds of time. On one side was the slow time of evolution, in which populations changed across generations. On the other was the sudden time of physics, in which a planetary environment could be disturbed faster than biological adaptation could respond. That difference would shape everything that followed. The impact site also mattered. The asteroid struck a region near what is now the Yucatan Peninsula, where the target rocks included materials that could release large amounts of vapor, dust, and sulfur-bearing compounds when subjected to extreme heat and pressure. Researchers continue to refine exactly how those materials were distributed and how much each contributed to later climate effects. But the broad connection between the impact, atmospheric disturbance, and mass extinction is strongly supported. In the final approach, however, none of those later consequences had yet unfolded. There was still sunlight over much of the planet. Marine food webs were functioning. Forest canopies were intact across vast areas. Dinosaurs still occupied ecosystems that had supported their lineages for millions of years. Birds, mammals, insects, reptiles, amphibians, plants, and microorganisms continued ordinary biological processes. The future difference between survival and extinction had not yet been expressed. It was contained only as possibility inside the relationships between bodies and environments. A species dependent on abundant fresh vegetation would face a different future from one able to survive on stored food, detritus, seeds, or small prey. An organism exposed on the surface would experience some disturbances differently from one sheltered underground or in water. A population near the impact region would face hazards that distant populations might initially escape. These differences would become important later, but they were already present before the first rock was shattered. The final minutes were therefore not a global scene of visible destruction. They were a moment when an existing world still functioned normally, while the physical conditions capable of ending much of its evolutionary history were approaching from above. The asteroid had not yet killed anything through impact. Yet the path toward one of the largest biological turnovers in Earth's recent geological history had narrowed to a distance that was disappearing second by second. Human beings would not appear for tens of millions of years, but the continuity of the mammalian branches from which primates later emerged would eventually depend on what survived beyond this boundary. The next decisive instant would not take generations, centuries, or even hours. Once contact occurred, the slow biological world would be forced to respond to a physical event unfolding on a timescale life had no opportunity to negotiate. At the instant the Chicxulub impactor reached Earth, the familiar behavior of solid rock changed almost beyond recognition, not because stone literally became ordinary liquid, but because the pressures and temperatures generated by the collision were so extreme that the crust could deform and flow in ways that are impossible under everyday conditions. The asteroid and the rocks beneath it were compressed by a shock wave moving through matter at enormous speed. Minerals were fractured, crystal structures were damaged, and some material was heated enough to melt or vaporize, while other rock was pushed outward and downward as the developing crater began to open. This process happened so quickly that there was no gradual transition from an intact landscape to a damaged one. The energy carried by the incoming body was transferred into the ground almost immediately, sending intense pressure through the target rocks and transforming a once stable region into a rapidly expanding zone of excavation, melting, fragmentation, and motion. Geologists can recognize traces of these conditions because certain minerals preserve microscopic evidence of shock, including distinctive deformation produced only under pressures far beyond those generated by ordinary erosion, burial, or volcanic activity. Such evidence has become one of the important ways scientists identify large ancient impacts. Alongside the buried crater itself and material deposited around the same geological boundary, the phrase that rock behaved like a fluid is therefore a useful description of what extreme pressure can do. But it should not be mistaken for the idea that the entire crust simply turned into a sea of molten stone. Different materials experienced different pressures and temperatures depending on their location. Some were vaporized, some melted, some fractured into fragments, and others were displaced while remaining largely solid. The result was a rapidly changing structure in which enormous masses of rock moved outward from the point of contact and deeper material was temporarily displaced, creating what researchers call a transient crater before gravity began reshaping it. The details of this process are reconstructed through drilling, geophysical measurements, laboratory studies, and computer models rather than direct observation, so individual estimates continue to be refined, yet the overall physical sequence is well established. A high-velocity collision produced shock compression, excavation, melting, and large-scale movement of the crust, and the effects did not remain confined to the place where the asteroid touched the ground. Material thrown upward would become one route by which a local impact began influencing a much larger world. This sudden transition also matters to the distant origins of human beings because the mammalian lineages alive at the time depended on landscapes that had always seemed stable on the scale of an individual lifetime. Their bodies had evolved under gravity, ordinary temperature ranges, familiar soils, vegetation, water, and seasonal change. None had adaptations for a moment when bedrock itself could be shattered and displaced across a vast region. Survival, therefore, could not come from meeting the impact directly. It would depend on whether populations existed far enough from the most extreme physical destruction, and whether their ordinary traits happened to remain useful afterward. This distinction separates geological catastrophe from biological response. The rock could be transformed in seconds, but the fate of species would unfold through the consequences that spread from that transformation. Near the impact site, the physical damage was overwhelming. Farther away, the first signs could arrive through seismic disturbance, atmospheric effects, falling debris, or later changes in climate and food supply, which means the mass extinction cannot be reduced to the crater alone. The crater was the beginning of a chain, not the complete explanation. And understanding that chain requires following the energy as it moved from the collision into the crust, the atmosphere, the oceans, and eventually into living systems. What began as a moving asteroid had become shock waves, heat, broken minerals, molten rock, vapor, and ejecta. While above and beyond the devastated region, most of the planet still continued through the same day, unaware in any biological sense that the physical foundation of its future had already been altered. The Earth itself remained whole, but a small region of its crust had just experienced conditions powerful enough to begin changing the evolutionary direction of life far beyond the crater. The Chicxulub crater did not appear as a simple circular hole cut into the land. surface, and left unchanged. The collision created a structure through several stages that unfolded very quickly, beginning with intense compression and excavation, and followed by the movement of enormous volumes of rock under gravity. At first, the impact forced material downward and outward, producing what geologists describe as a transient crater, a temporary cavity much deeper and less stable than the final structure preserved today. Rock that had been buried far below the surface was displaced, while material closer to the point of contact was shattered, melted, vaporized, or thrown away from the growing cavity. The scale of this movement was immense, but the important idea is not a single exact measurement. It is that the impact rearranged the crust across a region large enough to leave a geological structure still detectable tens of millions of years later. Gravity then began to modify the temporary cavity almost immediately. The steep walls could not remain standing, so sections collapsed inward. Deep material that had been compressed and pushed downward began rebounding upward as the enormous pressure of the impact was released. In very large impact craters, this rebound does not simply create one permanent mountain in the center. The uplifted rock can rise, collapse, and spread outward, forming a circular zone of elevated material known as a peak ring. Chicxulub contains such a structure, and drilling into the buried crater has provided researchers with direct samples of rocks that were once located much deeper in Earth's crust. Their presence closer to the surface is evidence of the extraordinary motion generated during crater formation. The landscape created during those moments would have been unlike anything produced by ordinary erosion, earthquakes, or volcanic activity. Yet much of it did not remain exposed. Over the following millions of years, sediments covered the crater, and younger geological processes concealed much of its shape. Today, the structure lies partly beneath the Yucatan Peninsula and partly beneath the Gulf of Mexico, so its discovery required scientists to combine geophysical observations, drilling results, gravity measurements, rock chemistry, and evidence from the global geological record. This buried nature is one reason the crater was not immediately obvious to earlier generations of researchers studying the extinction. The connection between the impact structure and the end Cretaceous extinction became increasingly clear as evidence accumulated from different fields. That connection matters to the distant history that eventually led to human beings, because the crater represents more than a scar in the crust. It records the physical starting point of environmental changes that would reshape which lineages survived into the next geological age. The mammals alive then were not protected by any special evolutionary destiny. Many individuals and species disappeared alongside other organisms. The lineages that persisted did so within a world whose ecological structure had been altered, and their later descendants would diversify under conditions that no longer included the same dominant communities of large, non-avian dinosaurs. The crater, therefore, marks a boundary between a physical event lasting moments and biological consequences extending far beyond those moments. Rock movement near Chicxulub occurred extremely quickly, but ecological recovery would take far longer. This difference in timescale is essential when considering the claim that 75% of species were killed in a single day. The crater itself could form within a short period, and catastrophic destruction could spread outward rapidly. But species extinction is measured through the disappearance of populations and lineages, not simply through the number of individual organisms killed at the instant of impact. Some populations near the crater would have had almost no possibility of surviving the immediate physical effects. Populations on distant continents might have survived that day and still face severe environmental stress later. The crater was therefore the engine of the crisis, not a complete map of where and when every organism died. Its formation also launched material into the atmosphere, disturbed water, generated seismic energy, and exposed rocks to pressures and temperatures that changed their physical and chemical state. Each of those consequences created another pathway through which the impact could move beyond the Yucatan region. The crater that remained after the first chaotic movements was not merely a hole left by an asteroid. It was the final shape of an enormous transfer of energy through Earth's crust, a record of rock being compressed, excavated, uplifted, collapsed, and reorganized in a short interval. Long after forests returned and new ecosystems developed, that buried structure remained beneath younger sediments. Much later, a species descended from mammalian survivors would learn how to detect it and connect it with a thin global layer, marking one of the great biological transitions in Earth's history. The crater itself could not explain every death that followed, but without understanding how it formed, the larger extinction event remains impossible to understand. When the Chicxulub impact excavated the crust beneath what is now the Yucatan Peninsula, enormous quantities of broken, melted, and vaporized material were driven away from the collision zone. Some debris traveled outward through the atmosphere, while faster fragments were launched onto trajectories that carried them far above the surface before gravity pulled them back to Earth. The phrase, "thrown beyond the atmosphere," can sound as if the planet permanently lost most of this material to space. But that is not what the evidence requires. Much of the ejecta remained gravitationally bound to Earth and eventually returned after traveling great distances from the crater. The important point is that the impact carried energy and matter far beyond the region physically struck. Around the world, geologists have identified material associated with the Cretaceous-Paleogene boundary, including tiny glassy droplets formed from molten rock and minerals that record intense shock. These traces show that the collision was not merely a local disturbance. Some molten droplets cooled while moving through the atmosphere and fell back as small spherical particles. Fine dust and vaporized material could remain aloft longer than heavy fragments. Their later effects depended on particle size, composition, altitude, and atmospheric circulation. Scientists continue to refine estimates of how much material occupied different layers of the atmosphere, so it is safer to describe the broad process than to pretend every detail is known precisely. What is well supported is that a great volume of material was rapidly displaced. Some reached very high altitudes, and returning debris carried the consequences of the impact across a wider area. For living organisms, distance from Chicxulub no longer meant complete separation from the event. An animal on another continent might have escaped direct destruction near the crater, yet the atmosphere above it belonged to the same planetary system. Material lofted high enough could travel across regions never physically connected to Yucatan. The crater was geographically limited, but the paths taken by ejecta were not. The same principle would later matter for sunlight, temperature, and food webs, because the atmosphere could distribute effects over greater distances and longer periods. The connection to the distant origin of humans lies in this change of scale. Mammalian populations far from the impact site were not necessarily exposed to the same immediate hazards as animals nearby, but their future depended on what happened when the atmosphere and ecosystems around them changed. Their survival was not a victory over the asteroid itself. It was survival within transformed environmental conditions. Some individuals may have been protected by geography, shelter, water, or ordinary behavior, while others faced lethal conditions despite being far from the crater. These possibilities should not be turned into a precise story for any one animal, because the fossil record does not preserve such personal moments. What it does preserve is the larger pattern, a sharp geological boundary, widespread impact-related material, and major biological turnover associated with the same interval. Returning ejecta also converted motion back into heat as particles encountered the atmosphere, although the exact extent of thermal effects remains under study. There is evidence for widespread fires, but it is not necessary to claim that every forest on Earth ignited simultaneously. The stronger picture is one of severe but uneven consequences. Some areas experienced direct devastation. Others encountered falling material, fire, seismic disturbance, or large waves. Still, others may have survived the first hours with less local damage, only to face atmospheric and ecological changes later. This unevenness is essential for understanding both extinction and survival. A planetary catastrophe does not need to kill every organism in the same way or at the same moment. By the time much of the ejecta began returning, the original asteroid was no longer a single object. Its energy had become shattered crust, molten droplets, vapor, dust, shock, heat, and motion, creating pathways that connected one crater with the rest of the living world. The moment Chicxulub struck, the disturbance did not remain confined to the crater, because part of the impact energy entered the ground as seismic waves that traveled outward through the crust, shaking a region far larger than the place where the asteroid made contact. These waves were not identical to an ordinary earthquake produced by movement along a fault, because their source was a sudden transfer of energy from a high-velocity collision. Yet the ground transmitted vibrations through rock in different forms and at different speeds. Close to the impact site, the shaking would have been extreme. Slopes could fail, sediments could be disturbed, and unstable ground could collapse. While farther away, the motion would weaken but still leave traces in environments capable of preserving disturbance. Geologists studying rocks of the same age have found evidence consistent with severe seismic effects beyond the crater, including disrupted sediments and deposits that appear to record movement of water and ground. Although scientists cannot reconstruct the exact experience of every location or assign one certain earthquake magnitude to the event, the broad conclusion is secure that the collision generated extraordinary seismic disturbance. This matters because the first hour after impact was already becoming a story of transmission. The asteroid had stopped as a coherent body, but its energy continued moving through rock, air, water, and ejecta, connecting regions that had not been physically struck. Seismic waves could reach distant areas before slower environmental consequences developed. And in coastal or shallow water settings, the shaking could interact with unstable sediments and changing water levels, creating hazards. The result was not one uniform ring of destruction expanding evenly across the planet. Geography mattered, rock type mattered, distance mattered. Some places would have experienced greater disruption than others. This unevenness matters because organisms did not face a single identical catastrophe. An animal close to the impact region could encounter overwhelming physical destruction, while another far away might survive the shaking and later confront falling debris, darkness, cooling, or loss of food. The same distinction applies to the distant mammalian lineages from which primates would eventually emerge. Survival depended partly on where populations lived and whether local habitats remained usable as consequences arrived. No mammal understood the geological event beneath it, and no lineage was protected by a future role in human evolution. They were simply populations distributed across landscapes, exposed unequally to a crisis spreading through planetary systems. The shaking also reminds us why the extinction cannot be reduced to a single image of an asteroid hitting the ground. The collision was only the source. Once energy entered Earth, it moved through several channels at once. Seismic waves propagated through the crust. Atmospheric disturbances traveled above the surface. Ejecta moved through the sky, and displaced water began responding near the impact region. Each process followed its own timing, so the first hour was not one event repeated everywhere, but many connected events unfolded at different distances and speeds. Forests far from Yucatan might still have been intact, while sediments elsewhere were being shaken. Marine organisms in remote waters could still be feeding normally even as disturbances traveled toward them. This is why the claim that roughly 3/4 of species disappeared during the extinction event should not be confused with the idea that all of those losses happened immediately. The first hour delivered extraordinary physical damage and began processes that would later weaken ecosystems. But extinction is the loss of lineages across populations, not simply the death of individuals during one shockwave. Chicxulub changed the conditions of survival, first by releasing energy, then by allowing that energy to move outward, and the shaking ground was one of the earliest signs that a collision at one point on Earth had already become a crisis, extending far beyond the crater. For distant life, surviving the shaking, therefore, did not mean that the catastrophe was over. When the Chicxulub impact struck near the edge of a shallow sea, enormous amounts of energy were transferred not only into rock and atmosphere, but also into water. And that displacement began another pathway through which the catastrophe could spread far beyond the crater. Seawater close to the impact site would have been violently disturbed as the crust was excavated and material was driven outward, while collapsing crater walls, displaced sediments, and falling debris added further motion to the surrounding water, producing very large waves that traveled away from the Yucatan region. Geological evidence from areas around the Gulf of Mexico records powerful disturbances at approximately the Cretaceous-Paleogene boundary, including unusual deposits containing mixtures of sediments and debris that are consistent with rapid movement of water. And researchers have also identified evidence much farther away suggesting that the impact generated waves capable of affecting distant coastlines. But reconstructing the exact height of every wave at every location is difficult because coastlines, ocean depth, seafloor shape, and later geological alteration all influence what is preserved. So it would be misleading to imagine one perfectly uniform wall of water circling the planet at a single height. The safer picture is of an enormous initial disturbance that produced complex waves whose effects varied greatly from place to place. Near the impact region, the consequences could have been overwhelming. While farther away, the energy would interact with continental shelves, bays, shallow seas, and coastlines in different ways. In some locations, water could rise rapidly, retreat, return, or carry sediment inland. And in enclosed or shallow basins, even seismic shaking itself could produce additional movement. This complexity is important because water does not respond to catastrophe as a passive surface. It carries energy, moves sediment, changes shorelines, and can destroy habitats that are otherwise far removed from the crater. Coastal ecosystems that had functioned normally before the impact could suddenly experience erosion, burial, saltwater intrusion, or the removal of vegetation and animals. Marine organisms living in shallow environments could be disturbed by changing currents and sediment loads, while deeper or more distant waters might initially experience less direct physical destruction. Once again, survival depended strongly on location, and that unevenness helps explain why the extinction event cannot be understood as a single instant when the same thing happened everywhere. The distant mammalian lineages that would eventually contribute to the ancestry of primates were scattered across different landscapes, and those living inland might avoid the most destructive waves, while populations near low coasts or river systems could face very different conditions. None of this implies that surviving a wave guaranteed long-term survival, because the most important global stresses were still developing through the atmosphere, climate, vegetation, and food webs. But in the first hours, water became one of the fastest ways for impact energy to reshape environments beyond the immediate crater. This also reveals why the geography of the late Cretaceous matters so much. Sea levels were higher than today, and large areas of some continents were associated with shallow marine environments, meaning coastlines and inland seas created extensive zones in which changing water could affect life. Yet the exact configuration of those environments differed substantially from the modern world, so modern maps cannot simply be used to imagine where every wave traveled. Scientists instead combine sedimentary evidence, reconstructions of ancient geography, physical modeling, and the known location of the crater to estimate the broad pattern of disturbance. Some models indicate that the impact generated an exceptionally powerful tsunami, but numerical details vary with assumptions about the impact and ancient ocean basins. What remains strongly supported is that enormous water displacement occurred and left geological traces consistent with severe regional and transoceanic effects. By this point, the asteroid itself had already ceased to exist as an intact incoming body. Yet its original motion had been transformed into many moving systems. The crust was shaking. Debris was traveling through the atmosphere. Heat was being generated, and water was moving outward across marine environments. These processes overlapped without reaching every place simultaneously, which means an organism could survive one hazard only to face another later, and this layered pattern is essential to understanding the eventual disappearance of roughly 3/4 of species. Because extinction was not produced by one wave, one fire, or one moment of impact. It emerged from several forms of environmental stress, arriving across different timescales. The waves of the first hours were therefore not the whole catastrophe, but they were another sign that the event was escaping the boundaries of the crater and entering the connected systems upon which life depended. Before the first day had ended, the region surrounding the Chicxulub impact site had already become physically different from the landscape that existed that morning. Not because every distant ecosystem on Earth had been destroyed, but because several powerful processes were transforming the area around the crater at the same time. Rock had been excavated and displaced. Sediments had collapsed. Seismic waves had shaken the ground. Enormous quantities of ejecta had moved through the atmosphere, and water had been pushed across shallow marine environments and coastlines. Close to the impact site, there would have been little continuity between the former landscape and what remained afterward. Surfaces that had supported vegetation, rivers, wetlands, and coastal habitats could be buried, eroded, fractured, or covered by newly deposited material. Farther away, the changes would become less uniform, with some places experiencing severe shaking or flooding, while others remained physically recognizable for a time. This uneven pattern is essential, because the first hours of the catastrophe did not produce a single identical world everywhere. Distance from Yucatan, local topography, the position of coastlines, the nature of the underlying rock, and the direction in which ejecta and water moved all influenced what happened in a particular region. Some organisms may have died through direct physical destruction. Others could survive beneath soil, inside burrows, in freshwater environments, or in places that happened to avoid the most violent immediate effects. But survival through those hours did not mean that normal ecological conditions would return when the ground stopped shaking. The larger danger was that the physical damage of the first day was beginning to interact with processes that could persist much longer. Fires could remove vegetation from some landscapes. Disturbed sediments could alter rivers and coastal habitats. Atmospheric particles could influence the amount of sunlight reaching the surface. And the destruction of local food sources could begin affecting animals that had escaped the initial impact. This was the point at which the catastrophe started changing from a problem of immediate physical survival into a problem of ecological survival. And that distinction reaches directly toward the distant history of human origins. The mammalian lineages alive at the end of the Cretaceous were small pieces of much larger communities. Their continued existence depended not simply on whether an individual avoided a shock wave or flood, but on whether enough members of a population could find food, shelter, and opportunities to reproduce after the environment changed. Evolution operates through populations across generations, so the survival of a lineage required more than a few fortunate individuals enduring the first hours. If habitats disappeared across wide areas or food webs failed for long enough, even organisms that initially escaped could later decline. This is one reason the phrase that 75% of species were killed in 24 hours must be handled carefully. Geological evidence supports extraordinary destruction beginning immediately after the impact. But the disappearance of species from the fossil record reflects a broader extinction interval, not a reliable count of every lineage vanishing before the next sunset. The first day should therefore be understood as the opening of the crisis, the interval during which enormous amounts of energy were transferred into Earth systems, and many environments near the crater were rapidly transformed. By the end of those hours, the asteroid was no longer visible as a separate object, yet its influence was present in the crater beneath the surface, in disturbed coastlines, in ejecta falling across distant regions, in sediments moved by water, and in atmospheric material beginning to alter conditions far from Yucatan. The old Cretaceous world had not disappeared everywhere. Dinosaurs could still be alive on distant continents. Marine organisms could still be moving through oceans far from the Gulf region. Plants could still be standing beneath daylight, and small mammals could still be sheltering in familiar habitats. But the systems supporting those lives were entering conditions they had not experienced before. The importance of the first day lies precisely in this contrast. Much of life was still present, while the physical mechanisms capable of undermining that life had already been set in motion. The landscape near Chicxulub had changed visibly and violently, while the deeper planetary transformation was only beginning to spread through atmosphere, climate, vegetation, oceans, and food webs. So before the first sunset following the collision, Earth had crossed a boundary that many organisms had survived physically but would not survive ecologically. After the Chicxulub impact had hurled enormous amounts of material upward, gravity began bringing much of that debris back toward Earth, and this return transformed the sky into another pathway for destruction. Because fragments and droplets that had been accelerated away from the crater now carried energy back into the atmosphere, some pieces fell relatively close to the impact region, while others traveled much farther before descending. As fast-moving debris encountered the atmosphere, it lost energy through collisions with air molecules, heating both the particles and the surrounding air. And this process may have contributed to intense thermal conditions at the surface in some regions, but the exact global pattern remains a subject of scientific study, so it is important not to imagine the entire planet covered by one uniform sheet of fire. Geological evidence does support widespread burning near the end of the Cretaceous, including soot and charcoal in many deposits. Yet those traces do not prove that every forest burned at the same moment or with the same intensity. The safer conclusion is that returning ejecta added heat to an already damaged world and likely increased the risk of ignition where dry vegetation and local conditions allowed it, while other places may have experienced less severe thermal effects across the wider planetary system. The falling material itself also changed landscapes by covering surfaces with fine debris, glassy droplets, and fragments produced during the collision, and thin layers of impact material found far from Yucatan show how efficiently the event distributed matter across the planet. For animals that had survived the initial shock and shaking, the return of ejecta created another hazard that could arrive after the crater had already formed. A sheltered organism might avoid direct heat or falling fragments, while one exposed at the surface could face very different conditions. This unevenness would later matter to survival because populations scattered across different habitats did not all receive the same combination of stresses. The distant mammalian lineages from which primates would eventually descend were among those living through this changing mosaic, and there is no reason to think they possessed any special protection beyond ordinary traits that sometimes proved useful under harsh conditions. Small size, access to shelter, flexible diets, or the ability to exploit foods that remained available may have helped some populations, but such advantages would only matter if enough individuals survived and reproduced after the larger ecological disruption continued. The returning debris also demonstrates how quickly a local collision became a planetary event. The asteroid itself had struck one location, but its energy had already been converted into material, moving along countless paths through the sky, each fragment carrying a small part of the original disturbance away from Chicxulub. When those fragments returned, the impact was, in a sense, being redistributed across Earth, not as a second asteroid strike, but as heat, falling particles, atmospheric disturbance, and fresh damage to ecosystems already under stress. The distinction is important because it explains why the first day could be extraordinarily destructive without completing the entire extinction in that same interval. Some organisms were killed immediately, others survived the physical violence and later faced a world with damaged vegetation, unstable habitats, altered light, and disrupted food supplies. The return of ejecta, therefore, belongs to the transition between direct catastrophe and ecological crisis. It carried the violence of the crater into regions far beyond the point of contact, and helped create conditions in which surviving the morning did not guarantee surviving the weeks or months that followed. By the time much of this material had fallen back, the familiar sky had become part of the disaster itself, and the next danger would depend not simply on what was falling from above, but on how much of the living landscape below could continue to burn, recover, or provide food in a world whose atmosphere was already beginning to change. The idea that the entire surface of Earth caught fire immediately after the Chicxulub impact has appeared in many dramatic descriptions of the extinction, but the geological evidence supports a more complicated picture. There is strong evidence that fires occurred across many regions near the end of the Cretaceous, including layers containing charcoal and soot associated with the impact interval. Yet those traces do not demonstrate that every forest on every continent burned at the same time, or that the surface of the planet was exposed everywhere to identical levels of heat. Researchers have proposed several mechanisms that could have increased the danger of fire, including the intense thermal effects close to the impact region, and the heating associated with material returning through the atmosphere. But models differ in how much heat reached the ground at different locations, how long it lasted, and whether vegetation everywhere would have ignited. Local conditions would have mattered greatly. Dry plant material burns differently from wet vegetation. Dense forests respond differently from open environments, and clouds, geography, season, and the distribution of ejecta could all influence what happened in a particular region. This means that widespread fire is well supported, while a single global firestorm consuming every landscape is much harder to justify, and that distinction is important, because the extinction did not require every tree to burn in order for ecosystems to fail. Losing large areas of vegetation in combination with other stresses could already create severe problems for animals dependent on fresh plant growth, shelter, nesting sites, or stable local climates. Fires would also produce smoke and soot that could enter the atmosphere, adding another source of particles to a sky already disturbed by material from the impact. While burned landscapes would lose living plant tissue that normally captured sunlight and supported herbivores, insects, and many smaller organisms, even where vegetation survived the first day, later reductions in sunlight and temperature could place additional pressure on growth. So the biological meaning of fire was larger than the flames themselves. It was the removal of habitat and stored biological energy from parts of a food web already facing several simultaneous disruptions. For large herbivorous dinosaurs, this could become serious if broad areas of edible vegetation were damaged and new growth slowed. But smaller animals were not automatically safe. Insects, mammals, birds, reptiles, and amphibians also depended directly or indirectly on plants and on the structure that vegetation created. Some animals could exploit seeds, roots, detritus, aquatic foods, or sheltered resources that remained after surface damage, and these differences may have contributed to uneven patterns of survival. Although no single trait can explain every lineage that crossed the extinction boundary, this point leads quietly toward the distant beginning of our own story, because the mammalian branches that survived were not necessarily the strongest animals in their environments. They were members of populations whose ordinary biology happened to remain workable under conditions that eliminated many competitors and food sources. Surviving fire would have been only one challenge among many. A burrowing mammal might avoid intense surface heat, but later emerge into an environment with fewer plants, fewer insects, altered temperatures, and uncertain food. So protection from the first hazard did not guarantee survival through the ecological consequences that followed. The evidence for burning also helps correct another misleading interpretation of the first 24 hours. Enormous numbers of individual organisms may have died quickly in areas exposed to direct impact effects, fires, flooding, or falling debris. But a species disappears only when its populations fail to continue, and many populations far from the crater could have remained alive after the first day. The extinction therefore unfolded through a combination of immediate mortality and longer environmental collapse. Fires belonged to the first category and also helped intensify the second, because damaged vegetation and atmospheric soot could continue affecting ecosystems after flames had gone out. The world after Chicxulub was not divided simply into places that burned and places that remained untouched. It was a shifting landscape of different levels of disturbance, with some regions devastated, some partially damaged, and others initially spared, while all remained connected to an atmosphere and climate system that was entering a much broader crisis. And this is why the question of how much Earth actually burned has no scientifically responsible answer in the form of one dramatic global image. The stronger conclusion is more measured. And more important, widespread fires were one major consequence of the impact. But the extinction became global because fire was only one layer of a much larger breakdown in the environmental conditions that had supported Cretaceous life. The first great biological loss after the Chicxulub impact was not simply the death of individual animals, but the destruction and disruption of the places that allowed populations to continue living. Because a habitat is more than physical ground. It is a combination of food, shelter, temperature, water, vegetation, nesting sites, seasonal rhythms, and relationships with other organisms. When several of these supports fail together, an animal can survive the initial catastrophe and still lose the conditions necessary for long-term survival. Forests damaged by heat or fire could no longer provide the same amount of foliage, seeds, insects, shade, or protected spaces. Coastal environments disturbed by powerful waves could be buried beneath sediment or stripped of vegetation. River systems could receive large quantities of debris, and landscapes near the impact region could be transformed so completely that the biological communities that had occupied them no longer had a functioning environment to return to. Farther from Chicxulub, the damage was less uniform. Some forests probably remained standing, Some freshwater habitats remain usable, and many organisms certainly survived the first hours. Yet, survival itself did not restore the ecological connections that had been broken. A herbivore depended on plants that had to remain abundant enough to support repeated feeding. A predator depended on prey populations that needed to reproduce. Insects depended on vegetation and organic material, and plants depended on sunlight, water, temperature, soil, and the ability to grow through future seasons. When habitat damage removes several links at once, the effect can continue long after the original physical disturbance has ended. This is one reason mass extinction cannot be understood by imagining a single instant when most species simply fell dead. Populations can disappear gradually when their environment no longer supports enough individuals to survive and reproduce. The same principle is important to the distant origin of humanity, because the mammalian populations alive at the end of the Cretaceous were not surviving in isolation from their surroundings. Their future depended on whether they could continue finding food and shelter within damaged landscapes. Some small mammals may have benefited from habits such as burrowing or using varied food sources, but those possibilities should not be turned into a universal explanation. Different mammalian groups occupied different environments. Many disappeared, and survival depended on combinations of geography, ecology, chance, and traits that had evolved long before the impact. The lineages that eventually contributed to the ancestry of primates were therefore carried forward, not because they were destined to produce humans, but because enough populations in their broader evolutionary history passed through a world in which habitats were being reorganized. Habitat loss also changes the meaning of body size. An enormous herbivore may possess great physical strength, yet require large quantities of food across a wide range, while a smaller animal may survive on fewer resources or use shelters inaccessible to larger species. But even a small body offers no protection if food disappears entirely. Similarly, an aquatic organism may escape a forest fire, but still depend on water chemistry, oxygen, plants, insects, or food entering from surrounding land. Every refuge remained connected to other ecological processes, and those connections would become increasingly important as atmospheric effects developed after the impact. The first damaged habitats were therefore only the beginning of a wider crisis, because the same sky that carried ejecta and soot could later reduce the energy-reaching plants and microscopic organisms that formed the base of food webs. An ecosystem already weakened by physical destruction would have less capacity to absorb another period of stress. Recovery from a local fire normally depends on nearby surviving vegetation, seeds, animals, and relatively stable climate. But when disturbance occurs across many regions while atmospheric conditions are also changing, the sources of recovery can themselves be weakened. This difference helps explain why the Chicxulub event became more than a collection of regional disasters. It began altering the mechanisms through which damaged environments ordinarily rebuild themselves. And the distant mammalian survivors that ultimately stand somewhere deep behind the human story would inherit the consequences of that transformation. Not a clean, empty planet, but a fragmented biological world in which some communities persisted, others collapsed, and new ecological opportunities emerged only after immense losses. By the end of the earliest destructive interval, many organisms were still alive. Many habitats remained recognizable, and the majority of Earth had not been physically erased. Yet the relationship between living things and their environments had already begun to change. The catastrophe was moving away from the simple question of who survived the impact and toward the more difficult question of which populations could continue living once the places that supported them no longer worked in the same way. By the time the first day after the Chicxulub impact was unfolding, the danger to life no longer came from one source, because several forms of environmental stress were beginning to overlap. The ground had been shaken, coastlines and shallow seas disturbed. Ejecta had traveled through the atmosphere and returned. Fires had damaged vegetation, and dust, soot, and sulfur-bearing material had begun entering the sky. Each process could harm organisms, but their combined effect was more serious because ecosystems recover from disturbance by relying on resources that remain intact elsewhere. A burned forest can regenerate if surrounding vegetation survives. A flooded coast can be recolonized if nearby habitats still function, and an animal population can recover if food, shelter, and reproductive opportunities remain available. After Chicxulub, however, several of those supports could fail, creating a crisis in which recovery itself became more difficult. An organism that survived the shock wave might later encounter fire. An animal that escaped flooding might find its feeding ground damaged, and a population that avoided direct destruction could still depend on plants or prey in decline. This layering of hazards is one reason the first 24 hours matter so much. Not because all later extinctions were completed within that interval, but because the physical mechanisms capable of driving ecological collapse had already been set in motion. The atmosphere connected continents, the oceans carried disturbance across coastlines, and food webs linked large animals to processes occurring in plants, insects, plankton, soil, and water. The mammalian lineages that would eventually contribute to the ancestry of primates were caught inside the same web. They were not protected by small size alone, and they were not moving toward a predetermined human future. Some populations likely benefited from shelter, flexible feeding, or resources that remained available, while others disappeared. And the difference depended on local conditions and inherited biology. What mattered was whether enough individuals could continue living and reproducing as one stress followed another. Because evolution works through populations across generations rather than through the survival of a single fortunate animal. The same principle applied in the oceans, where an organism could be far from the crater and still become vulnerable if changing light, temperature, chemistry, or food availability weakened the system around it. Physical distance from Yucatan therefore reduced some immediate dangers without creating complete safety. The catastrophe had begun to operate through systems that covered the planet, and those systems did not need to kill every organism directly to transform the future of life. They only needed to push enough habitats beyond the conditions required by enough species for long enough periods. This is why the phrase 75% of life can be misleading if it is heard as 75% of all individual organisms dying together. The widely cited estimate refers more appropriately to the proportion of species lost across the extinction event. While the timing and pathway of disappearance differed among groups and environments, some individuals were killed within minutes or hours. Some populations may have persisted before declining, and some lineages crossed the boundary and later expanded into ecological opportunities created by the losses around them. Our own existence belongs distantly to that last category, because the later history of mammals, primates, and eventually humans depended on mammalian branches that continued beyond the crisis, but that survival should not be treated as evidence that mammals were superior. It resulted from an interaction between traits, geography, resources, chance, and environmental change. By the end of the first day, the most important transformation was not that Earth had become lifeless. It had not. Nor that every ecosystem had already collapsed. Many had not. The deeper change was that the planet had entered a condition in which several foundations of biological stability were being stressed simultaneously, and surviving the impact itself had become only the first test in a longer struggle for continuity. Within the first 24 hours after the Chicxulub impact, many organisms could have died through direct physical forces, but the disappearance of entire species followed a more complicated path. Animals and plants close to the impact region faced the greatest immediate danger from shock, heat, collapsing landscapes, displaced water, falling debris, and severe disturbance of habitats, while populations farther away might have experienced only some of those effects, or none of them during the first day. This difference matters because an individual can die in seconds, while a species becomes extinct only when all surviving populations eventually fail to continue. Geological evidence allows scientists to reconstruct the enormous scale of the impact and the environmental crisis associated with the Cretaceous-Paleogene boundary, but it does not provide a global clock showing exactly when every species disappeared. The famous estimate that roughly 3/4 of species were lost refers to the extinction event as a whole, not to a verified count of species eliminated before 24 hours had passed. Some organisms near Yucatan were almost certainly killed immediately. Coastal populations could be devastated by water movement and fires could destroy living communities across some regions. Yet on distant continents, many individuals could remain alive after the first day. Forests could still be standing in places. Freshwater habitats could still contain functioning communities, and marine organisms in remote waters could continue feeding even as the atmospheric consequences of the impact were beginning to develop. What these survivors did not yet know, in any conscious sense, was that survival of the first physical disturbance was only the beginning of a much longer ecological test. Sunlight would later become a central problem. Plant productivity could fall. Food chains could weaken. Temperatures could change. And populations already reduced by direct destruction might become more vulnerable to further losses. This distinction between immediate death and eventual extinction is essential to understanding the distant path toward human origins. The mammalian lineages that survived across this boundary were not simply animals that escaped the first day. They had to persist through later changes long enough to reproduce and maintain populations. A few sheltered individuals would not have been enough if their food sources disappeared or if their descendants could not survive the altered environment. The continuity that eventually allowed mammals to diversify, primates to appear much later, and human ancestry to emerge required survival across generations, not merely across hours. The same principle applies to the non-avian dinosaurs and many marine groups that disappeared. Their extinction cannot responsibly be reduced to one universal mechanism or one moment. Large body size, specialized diets, reproductive biology, habitat dependence, and the collapse of ecological networks may all have influenced vulnerability in different ways. But scientists should be cautious about assigning a single cause to every lineage. Some species may have declined rapidly, others may have persisted locally for a short period, and the fossil record rarely offers enough resolution to follow each population day by day. The first 24 hours were therefore extraordinary because they concentrated immense physical destruction into a very short interval. Yet their deeper importance came from what they initiated. The impact damaged environments, redistributed material, disturbed the atmosphere, and weakened systems that normally supplied energy to living communities. Those changes created conditions in which mortality could continue long after the crater had formed and the largest waves had passed. What could die in one day were countless individual organisms and perhaps entire local populations exposed to the most extreme effects. What cannot be demonstrated is that roughly 75% of all species on Earth vanished completely within that exact period. The scientifically stronger interpretation is that one day opened a global biological crisis whose consequences unfolded across different environments and different timescales. And this difference makes the event no less profound, because a single day did not need to finish the extinction in order to determine the direction in which much of life would soon be forced. The phrase that roughly 75% of life disappeared at the end of the Cretaceous can easily create the wrong picture, because it sounds as if 3/4 of every living thing on Earth died at once. But scientists usually mean something more specific The estimate refers broadly to the proportion of species that disappeared during the Cretaceous-Paleogene mass extinction, not to a measured percentage of individual organisms killed during the first day. And even that estimate represents a reconstruction from an incomplete fossil record rather than a perfect global census. Fossils preserve only a small fraction of organisms that once lived. Preservation differs between environments, and some groups leave much clearer traces than others. So paleontologists compare patterns across many rock layers and fossil communities to estimate the scale of biological loss. The result is still extraordinary. Entire branches of life vanished, including all non-avian dinosaurs, ammonites, many marine plankton groups, and numerous other organisms on land and in the oceans. But the losses were uneven. Some lineages suffered almost complete collapse, while others survived the boundary and continued into the Paleogene. This unevenness is one of the most important clues to how the extinction actually worked. If the event had simply killed a fixed fraction of organisms everywhere in the same way, survival would appear almost random. Instead, the fossil record suggests that ecology mattered, where organisms lived, what they ate, how dependent they were on primary production, how rapidly they reproduced, and whether they could use sheltered or relatively resilient habitats could influence their chances. Although no single trait explains every survivor, the meaning of 75% therefore belongs to biodiversity rather than to a single moment of mortality. A species could disappear because populations were killed directly, because surviving populations became too small, because food sources collapsed, because reproduction failed, or because environmental conditions remained unsuitable long enough that recovery became impossible. These pathways could unfold across different timescales, and the fossil record usually cannot resolve the exact day on which the final member of a species died. This distinction is especially important for the central question of the first 24 hours, because that day may have determined the direction of the crisis without completing every extinction. Enormous physical destruction had already occurred. Atmospheric material had already been injected into the sky. Habitats had already been damaged, and food webs had begun to lose some of the structures that supported them. But many organisms were still alive far from the crater. What followed would decide whether those survivors represented temporary remnants or populations capable of continuing across generations. The distant mammalian branches that would eventually lie behind primates and humans belong to this second story. They did not merely survive a violent day. Some of their populations survived the altered ecological world that followed, reproduced within it, and carried their lineages forward. This should not be interpreted as proof that mammals were inherently better adapted than dinosaurs in some general evolutionary sense, because many mammals also disappeared, and many dinosaur lineages had been successful for immense spans of time. Survival depended on the particular crisis that occurred, not on a universal ladder of biological superiority. The same reasoning applies to birds, crocodilian relatives, turtles, amphibians, fish, and other groups that crossed the boundary in varying proportions. Their persistence tells us that extinction filtered life rather than simply reducing everything equally, and the filter was created by environmental conditions set in motion by the impact. This is why the number 75% is most useful when treated as a measure of evolutionary loss. Not as a dramatic stopwatch. Imagine the history of life as a branching tree, with every species representing one twig connected to deeper branches. The extinction did not merely remove individual leaves, it cut away large parts of that tree. Some branches ended completely and could never return, while others passed through the crisis and produced new branches later. Human beings exist on one very distant branch that could only develop because earlier mammalian lineages remained unbroken. Yet the event was not arranged to make that outcome possible. It removed possibilities as much as it created opportunities. Worlds that might have developed from extinct lineages were lost permanently, while surviving lineages entered environments with altered competition and newly vacant ecological roles. The real meaning of 75%, therefore, lies not in imagining a planet suddenly reduced to 1/4 of its living bodies, but in recognizing how much evolutionary diversity disappeared from future history and how profoundly the balance between surviving lineages was changed. The first day opened that loss by transforming the physical environment. The following interval turned physical disturbance into biological extinction, and the world that eventually allowed mammals, primates, and humans to emerge was built not from a clean beginning, but from the surviving fragments of a much older biosphere whose structure had been permanently reduced. After the first violent hours of the Chicxulub impact, some of the most important consequences were no longer visible as broken rock, waves, or fire, because the atmosphere itself had begun to carry the crisis across the planet. The collision struck rocks in the Yucatan region that included sulfur-bearing minerals and other materials capable of producing gases and fine particles when heated and disrupted at extreme pressure, while fires and impact debris added soot and dust to the air. These substances did not all behave in the same way. Larger particles fell relatively quickly, finer dust could remain suspended longer, and sulfur compounds could form aerosols capable of reflecting sunlight back towards space. The precise quantities and residence times remain subjects of scientific refinement, so it would be misleading to claim that every atmospheric effect is known exactly, but the central conclusion is strongly supported. The impact injected enough material high into the atmosphere to reduce the amount of sunlight reaching Earth and to disturb climate on a global scale. This change was fundamentally different from the immediate destruction near the crater, because a shock wave weakens with distance, and a tsunami follows particular coastlines and ocean basins. While atmospheric particles can spread across vast regions and influence places that experienced little direct physical damage, a forest on another continent did not need to be burned by the first thermal effects in order to become vulnerable later. If sunlight weakened and temperatures fell, plant growth could slow even where trees remained standing, and marine ecosystems could face similar problems, because many food webs began with microscopic organisms near the sunlit surface of the ocean. Soot from widespread fires may also have contributed to reduced light, although its exact importance relative to sulfur aerosols and other impact material continues to be studied. What matters biologically is that several forms of atmospheric disturbance were occurring together. Some particles absorbed or scattered light, sulfur aerosols reflected part of the incoming solar energy, and the combined effect could shift Earth away from the warm conditions that had characterized the late Cretaceous. The atmosphere had therefore become a mechanism that transformed one regional collision into a planetary environmental problem, and this transition helps explain why populations far from Chicxulub could eventually disappear even if they survived the first day without direct injury. Their danger would increasingly come from changes in energy entering ecosystems rather than from the asteroid itself. The distant mammalian lineages that would much later contribute to primate ancestry were living inside these same systems. They depended on food that ultimately traced back to photosynthesis or to organisms sustained by it, and they could not escape the consequences simply by being small or sheltered. A burrow might reduce exposure to heat or falling debris, but it could not produce new food if the surrounding ecosystem stopped functioning normally. Some animals may have survived by using seeds, detritus, insects, freshwater resources, or other foods that remained available. Yet those possibilities varied between species and regions and should not be treated as a universal survival formula. What the atmospheric changes did was alter the basic conditions under which all of these strategies operated. Sunlight is not merely something organisms experience as brightness. It is the main external energy source supporting most surface ecosystems. When less solar energy reaches plants and photosynthetic plankton, the consequences can move upward through food webs, even if large animals are not immediately harmed by the darker sky itself. This is why the atmospheric stage of the catastrophe was potentially more important for global extinction than many of the spectacular events that occurred during the first minutes. The crater was local. The largest waves were geographically structured, and fires were uneven, but reduced sunlight and cooling could influence broad areas at once, creating a shared environmental stress across continents and oceans. By this point, Earth was still very much alive. Many forests remained. Many animals still moved through familiar habitats, and the ocean still contained functioning communities. Yet the atmosphere above them was no longer simply carrying ordinary weather. It contained the products of an impact capable of changing how much energy reached the surface, and once that happened, the crisis moved beyond the question of who had survived the collision. Because the future now depended on whether ecosystems could continue supporting life under a sky that was becoming darker and colder than the world beneath it had been adapted to endure. As dust, soot, and sulfur-bearing materials spread through the atmosphere after the Chicxulub impact, the crisis entered a quieter but potentially more destructive phase. Because the greatest danger was no longer limited to places struck by waves, heat, fire, or falling debris. Instead, the amount of sunlight reaching the surface began to decline, and with less solar energy entering the lower atmosphere and the oceans, temperatures could fall across large areas of the planet. Researchers often describe this interval as an impact winter, although it should not be imagined as a normal winter arriving everywhere in the same form. The magnitude and duration of cooling depended on how much material reached different atmospheric layers, how long aerosols and particles remained suspended, how rapidly they were removed, and how the climate system responded. Computer models differ in some details, yet they broadly support a period of severe reduction in sunlight and substantial cooling after the impact. Sulfur, released from rocks at Chicxulub, was especially important because sulfur compounds could form reflective aerosols high in the atmosphere. Sending part of incoming sunlight back towards space, fine dust and soot could contribute additional darkening, and the combined effect could disrupt a warm, late Cretaceous climate much faster than most organisms could adjust. The biological problem was not simply cold itself. A dinosaur, bird, mammal, reptile, or fish could potentially tolerate short periods outside its preferred temperature range, but entire ecosystems depended on regular energy arriving from the sun. Plants required light to maintain photosynthesis. Microscopic marine producers depended on sunlight in surface waters, and when these foundations weakened, the consequences could move upward through food webs. Herbivores might initially continue feeding on vegetation that remained. Predators could continue hunting surviving prey, and small animals might consume seeds, insects, dead organic matter, or stored resources, but these supplies were finite. And if new biological production slowed severely, every level above the producers would eventually face scarcity. Cooling could also change rainfall, growing conditions, and the seasonal patterns under which late Cretaceous ecosystems had evolved, creating stress even in regions that had escaped the spectacular destruction of the first day. This is why the impact winter helps connect the sudden collision with extinction occurring beyond the first 24 hours. The asteroid delivered its energy in moments, but atmospheric changes allowed that energy to continue influencing life long after the crater stopped forming. An animal thousands of kilometers from Yucatan might never encounter a tsunami or large falling fragment, Yet it could still live beneath a darker sky and within a food web receiving less energy than before. The distant mammalian lineages that eventually contributed to the ancestry of primates were subjected to the same basic limitation. Their small bodies did not create sunlight, and shelter underground could protect against immediate surface hazards without solving the longer problem of declining food. Some populations may have persisted because they could use foods less dependent on fresh green vegetation, exploit sheltered habitats, or reproduce under difficult conditions. But scientists cannot reduce survival to one simple trait. Many mammals disappeared as well, and the branches that continued did so through a combination of biology, geography, ecological flexibility, and circumstance, rather than through any predetermined path toward humans. The impact winter also differed from an ordinary seasonal winter because ecosystems had not evolved around a predictable return of conditions after a familiar number of months. Organisms could not rely on inherited seasonal timing to tell them when normal sunlight would return, and plants damaged by fire or cold faced difficulties regenerating if light remained weak. Forests ordinarily recover because surviving vegetation and seeds receive enough energy to grow again. But a widespread reduction in sunlight could slow that recovery across many regions at once, reducing the refuges from which animals and plants might recolonize damaged environments. Oceans faced a parallel problem near the surface, where photosynthetic microorganisms formed a major source of energy for marine ecosystems. If their productivity declined sharply, animals that never experienced direct physical effects of the impact could still encounter diminishing food as the disruption moved through trophic relationships. The exact severity varied among environments, and some freshwater or detritus-based systems may have been more resilient than others, which helps explain why survival was uneven rather than absolute. Earth did not become completely frozen, nor did all photosynthesis necessarily stop everywhere for one identical interval. The evidence instead supports a severe global disturbance in which reduced sunlight and cooling placed extraordinary pressure on ecosystems already damaged by fire, flooding, habitat loss, and direct mortality. By then, the first day had become only the opening moment of a longer biological crisis, and the same event that had shattered rock at Chicxulub was now influencing life through something almost invisible, a reduction in the sunlight that had powered the planet's food webs for hundreds of millions of years. Once sunlight became limited after the Chicxulub impact, the crisis reached the foundation of most ecosystems, because photosynthesis was the process that converted solar energy into the biological energy used by plants, algae, and many microorganisms. And nearly every large food web depended on that conversion, either directly or indirectly. The problem was not that every plant or photosynthetic organism died immediately, but that reduced light could sharply limit the rate at which new organic matter was produced. Forests that had survived fire or flooding still required sunlight to maintain leaves and replace damaged tissues. Aquatic plants still needed light in shallow waters, and microscopic organisms near the ocean's surface could continue supporting marine food webs only if enough solar energy reached them. When that flow of energy weakened, the effect could spread upward even toward animals that never depended directly on plants. Herbivores might continue feeding for a time on remaining vegetation. Predators could continue consuming surviving prey. Scavengers could use carcasses produced by the catastrophe. And smaller organisms could exploit seeds, roots, detritus, fungi, insects, or other stored resources. But these were reserves from an earlier biological world, and if photosynthesis remained strongly reduced, the system could consume those reserves faster than they were replaced. This is why the decline in sunlight was potentially more important for long-term extinction than many of the visually dramatic events surrounding the impact itself. A wave can pass, a fire can eventually stop, and seismic shaking fades. But a food web cannot function indefinitely without a continuing source of energy. The consequences would not be identical everywhere, because different ecosystems depended on fresh photosynthetic production to different degrees. Some freshwater environments and communities based partly on decaying organic material may have retained food longer than exposed terrestrial systems, while seeds and underground plant structures could survive conditions that killed leaves above the surface. And some marine environments may have been affected differently according to depth, circulation, and the organisms present. These variations are important because they offer a better explanation for selective survival than the idea that one type of animal simply possessed superior biology. The mammalian lineages that eventually contributed to the much later origin of primates were among organisms passing through these changing food networks, and their survival did not mean mammals somehow escaped dependence on the sun. They still ate organisms or materials whose energy ultimately came from photosynthesis. But some small mammals may have been able to use food sources that remained available when fresh vegetation became scarce, while sheltering behaviors and relatively low absolute food requirements could have helped certain populations under particular conditions. None of those traits guaranteed survival, and many mammalian lineages disappeared, which is why the later rise of mammals should be understood as survival through a specific ecological filter, rather than proof of evolutionary superiority. The same logic helps explain why large body size could become a disadvantage under prolonged scarcity. A large animal requires substantial energy simply to maintain its body, and if primary production falls, the amount of food needed to support large populations becomes harder to sustain. Yet body size alone cannot explain every extinction because diet, habitat, reproduction, geography, and local survival also matter. In the oceans, the weakening of photosynthetic microorganisms could produce equally serious consequences. Many marine food webs depended on plankton living in the sunlit upper layers, and a decline near the base could eventually affect organisms far above them, including animals that had survived the immediate disturbance without injury. Fossil evidence around the Cretaceous-Paleogene boundary records major changes among several groups of marine plankton, supporting the broader picture of a severe disruption to ocean productivity. Though the exact pattern differed among groups and locations, the crucial point is that extinction could proceed quietly after the violence of impact had faded. An animal did not need to be struck by debris or surrounded by fire to become vulnerable. It only needed to live inside a food web that could no longer replace the energy being consumed, and this slow transfer of scarcity from producers to consumers helps explain why the first 24 hours could initiate a catastrophe whose biological consequences extended far beyond that first day. By then, the central struggle was no longer simply against heat, shaking, or waves. It was against the weakening of the basic process that had supported complex life at Earth's surface for immense spans of time. And once photosynthesis became restricted across broad regions, survival depended increasingly on which organisms could endure, while the living world operated on the biological reserves left from before the sky grew dark. As the atmosphere darkened after the Chicxulub impact, plants on land entered a crisis different from the fires, floods, and direct destruction of the first day, because even vegetation that remained standing still depended on sunlight to maintain growth. Repair damaged tissue, produce seeds, and support the animals that fed on it. Reduced light meant reduced photosynthesis, and reduced photosynthesis meant less new biological energy entering terrestrial ecosystems. The effect would not have been identical everywhere. Some plants were buried or burned. Others survived below ground as roots, seeds, or protected tissues. And some environments may have retained enough light and moisture for limited growth, but across broad areas, the productivity of vegetation would have weakened. This mattered because large herbivores required continuous access to substantial quantities of plant material, while smaller herbivores also depended on leaves, seeds, stems, roots, or insects associated with vegetation. When fresh growth slowed, animals could initially consume what remained from before the impact. Yet those resources were finite. Standing leaves could be eaten, dead plant material could decay, stored seeds could be consumed, and damaged forests could not instantly replace what had been lost. The decline, therefore, moved through time, rather than appearing as one immediate collapse. A population might survive the first days while becoming less capable of surviving what followed. And this gradual exhaustion helps explain why extinction cannot be reduced to a single violent day. The first 24 hours damaged the physical world, but the following period tested whether ecosystems could continue producing enough food for the populations that remained. The connection to the distant origin of humans lies inside this transition, because the mammalian lineages that eventually gave rise to primates did not survive by escaping dependence on plants. Their food also came from ecosystems powered by photosynthesis, either directly through plant material or indirectly through insects and other animals. Some small mammals may have endured because they could use a wider range of foods, but this was not a universal advantage, and many mammalian groups disappeared. What mattered was the relationship between body size, diet, shelter, reproduction, geography, and usable food. Large herbivorous dinosaurs faced a serious problem if broad areas could no longer produce enough vegetation to meet their energy needs. Yet it would be too simple to say that large size alone caused their disappearance, because the fate of any lineage depended on several interacting pressures. Plants themselves also varied in resilience. Seeds can remain dormant, roots can survive beneath damaged surfaces, and some vegetation can recover rapidly when light and temperature improve. While other plant communities take longer to rebuild, fossil evidence from the boundary indicates major disruption in vegetation, followed by recovery patterns that differed across regions, including intervals in some places where ferns became especially abundant after disturbance. These patterns show that terrestrial vegetation was not erased permanently, but it was reorganized in ways that changed the amount and type of food available to animals. This ecological reorganization became one of the filters through which survival passed, because an animal adapted to a narrow diet could be more vulnerable if that resource disappeared, while another able to consume several kinds of food might continue longer. Even then, survival required more than individual flexibility. Enough members of a population had to remain alive, reproduce, and raise offspring under unstable conditions. This is where environmental damage could become evolutionary loss. Once plant productivity fell, every consumer above it was forced to draw from a shrinking energy supply, and the consequences spread upward through herbivores, omnivores, predators, scavengers, and decomposers. The Cretaceous had supported enormous biological communities because sunlight continuously replenished the base of those systems. After Chicxulub, that flow was interrupted, not everywhere and not forever, but long enough to make survival a problem of energy rather than simply endurance. And the world that emerged afterward would be shaped by which lineages could persist until ecosystems began to recover. As plant productivity declined and herbivore populations came under increasing pressure, predators faced a different kind of crisis because their survival depended on the continued availability of prey, and a predator can endure only as long as enough energy continues moving upward through the food web. Large carnivorous dinosaurs may have survived the immediate impact in some regions, but if the animals they hunted became fewer, weaker, or more widely scattered, the energy required to find and capture food would become harder to replace. Smaller predators face the same basic problem at a different scale, because insects, small vertebrates, eggs, and other prey could also decline when vegetation and habitat structure changed. This meant that the effects of reduced photosynthesis did not stop with herbivores. They continued upward through trophic relationships, turning a shortage at the base of the food web into scarcity among animals that never ate plants themselves. Predators could temporarily survive by feeding on carcasses produced by the catastrophe, and scavenging may have provided short-term resources in some environments, but dead animals are not a renewable food supply. Once the initial abundance of carcasses diminished, predators required functioning prey populations capable of reproducing, and those prey populations required functioning environments below them. This distinction is important because a food web can appear to remain alive even while the process that renews it has already weakened. For a time, there may still be animals to hunt, seeds to eat, insects to collect, and stored organic matter to consume. Yet if primary production remains low, every feeding event removes energy from a biological reserve that is not being replaced at its former rate. Eventually, the shortage becomes visible at higher levels, and populations that initially seemed protected by strength, speed, or hunting ability can begin to decline. This pattern helps explain why large predators are often vulnerable during severe ecological disruptions, because they generally require many prey organisms to support relatively few individuals at the top of a food web. But it would be misleading to claim that body size alone determines survival. Different predators had different diets, habitats, reproductive rates, and geographic ranges, and the fossil record cannot reconstruct the precise final days of every species. What can be understood more securely is the direction of energy loss. Less photosynthesis meant less plant production. Reduced plant production placed pressure on herbivores and smaller consumers, and fewer consumers eventually reduced the food available to predators. The same principle reaches toward the much later origin of humans, because the mammalian branches that survived did not stand outside this collapse. Carnivorous or insect-eating mammals also depended on prey sustained by lower levels of the ecosystem, while omnivorous species may have gained some resilience from being able to shift between different foods. But no feeding strategy guaranteed survival if local resources became too scarce. Some populations disappeared, others persisted, and the evolutionary lineages that later produced primates continued only because enough individuals remained through the period of ecological stress to reproduce across generations. The importance of this survival is often misunderstood. Mammals did not suddenly replace dinosaurs because they were waiting for an opportunity. They were themselves survivors of a severe biological filter. And only after the extinction had removed many established lineages did some surviving groups begin expanding into ecological roles that had become vacant. Before that expansion could occur, however, populations had to endure a world in which prey was disappearing and familiar food webs were becoming simpler, fragmented, or reorganized. Predators that were highly specialized on particular prey could face especially severe problems if those prey declined. While animals capable of scavenging or switching among food sources may have had more options, yet ecological flexibility was useful only where alternative resources actually existed. The collapse, therefore, unfolded differently from continent to continent and habitat to habitat, not as one synchronized moment when every predator suddenly starved. Some regions may have retained functioning communities longer than others, and freshwater environments or areas with stored organic material may have continued supporting certain food chains even while surrounding terrestrial systems weakened. This uneven survival is part of why mass extinction leaves a complex fossil pattern rather than a simple line dividing everything alive from everything dead. The first day had created extraordinary mortality, but the deeper biological loss came as networks of dependence stopped renewing themselves, and predators revealed this most clearly, because their decline showed that a catastrophe beginning with rock, heat, and atmosphere had now reached the upper levels of life through something much quieter. The disappearance of enough prey to make continued survival increasingly difficult. The oceans were not protected from the Chicxulub catastrophe simply because they lay far from the crater or because water could shield organisms from fire and falling debris, because marine ecosystems depended on the same flow of solar energy that supported life on land. And once dust, soot, and sulfur aerosols reduced the amount of sunlight reaching Earth, organisms living near the sunlit surface of the sea faced a serious decline in the conditions required for photosynthesis. Microscopic plankton formed an important foundation for many marine food webs, and when some groups of these primary producers suffered severe losses, the effects could move upward through animals that depended on them, directly or indirectly. Fossil evidence across the Cretaceous-Paleogene boundary shows major changes among marine plankton, including severe losses in several groups. While ammonites and various other marine organisms also disappeared, yet the oceans did not become empty, and the biological response was not identical everywhere. Some microorganisms survived, many fish lineages continued, and marine communities eventually recovered, which means the extinction acted as an ecological filter rather than simply destroying everything living in seawater. Reduced sunlight was only one source of pressure, because the impact also disturbed ocean chemistry. Sulfur compounds released into the atmosphere could eventually return to the surface, and changes in temperature, nutrient cycling, and the material entering the oceans could alter conditions experienced by marine organisms. Researchers continue to examine the relative importance and duration of these processes, so it would be misleading to describe one precise chemical sequence as equally severe in every ocean basin. The stronger conclusion is that marine ecosystems face several overlapping disturbances at the same time that their food production was being weakened. Organisms near the surface were particularly connected to sunlight, while communities in deeper water depended in many cases on organic material produced above and sinking downward. So a decline in surface productivity could eventually influence environments that never experienced direct darkness in the same biological way. This demonstrates again how the catastrophe could travel through ecological relationships rather than through direct physical contact. An animal did not need to be struck by ejecta to become vulnerable. It only needed to depend on food produced by organisms that were declining. And this principle also reaches toward the distant origin of human beings. Because the mammalian populations surviving on land were part of a planet whose terrestrial and marine systems were changing together, later human evolution would depend on descendants of those surviving mammals, but those lineages existed within a biosphere shaped by the same global redistribution of survival and extinction occurring in the oceans. There was no separate protected world waiting for mammals while marine life collapsed. Both environments were passing through different expressions of the same crisis, and the survival of one lineage depended on conditions specific to its habitat, diet, reproduction, and geography. Marine food webs reveal especially clearly why the first 24 hours cannot represent the complete extinction event. Many organisms in distant seas may have survived the initial day without encountering destructive waves or intense heating, yet they could still decline later as primary productivity fell and ecological relationships weakened. Plankton populations can respond rapidly to environmental change, and when organisms at the base of a food web become scarce, consumers above them may encounter shortages after a delay. Larger predators can therefore remain alive for some time, even when the system supporting them has already begun to fail. This delay resembles what happened on land as surviving vegetation, herbivores, and predators drew from biological resources produced before the impact. The ocean contained its own reserves and refuges, but those reserves were not infinite. Some ecosystems may have been more resilient because they relied partly on detritus or food sources less immediately dependent on fresh photosynthesis. And survival patterns in certain freshwater environments suggest that food chains based on stored or decaying organic matter may have offered advantages under reduced sunlight, though no single explanation applies to every surviving group. What emerged from the extinction was therefore not an ocean stripped completely of life, but an ocean whose biological structure had been sharply reorganized. Some branches ended permanently, while others continued and eventually diversified. And this selective survival matters because the modern oceans, like modern terrestrial ecosystems, descend from the lineages that pass through that boundary. The same event that altered the distant evolutionary landscape from which primates would much later emerge also removed marine possibilities that could never return. And by following the collapse from sunlight to plankton, and then upward through marine food webs, the extinction becomes easier to understand, not as one day when life simply died, but as a planetary failure of energy transfer in which many organisms survived the first violence, only to find that the living systems beneath them could no longer support the same world. Among the organisms that crossed the Cretaceous-Paleogene boundary, survival was not concentrated in the largest, strongest, or most dominant forms, and this is one of the clearest lessons of the extinction, because many of the lineages that continued were relatively small, able to use more than one kind of food, or capable of sheltering in environments that were partly buffered from the most severe surface conditions. These traits did not guarantee survival, and they did not operate in the same way for every group. But together they help explain why some populations could continue when enormous amounts of biological energy had disappeared from ecosystems. A small body generally requires less total food than a large one, which can become important when plant productivity falls and prey becomes scarce. An animal that needs only a modest amount of energy to survive a day can sometimes persist on scattered resources that would be insufficient for a much larger animal. Yet small size alone was not enough. Because many small species also vanished, the ability to find different foods may have mattered just as much. Organisms that depended narrowly on one abundant resource could become vulnerable if that resource collapsed, while animals capable of eating seeds, insects, detritus, carrion, roots, or several kinds of small prey could potentially shift between whatever remained available. Seeds may have been especially useful in some terrestrial environments because they can store energy produced before the impact, and some can remain viable through periods when fresh plant growth is limited. Decaying organic matter could also continue supporting insects, fungi, microorganisms, and animals that fed within detritus-based food chains, allowing some ecological pathways to function even while fresh photosynthesis was greatly reduced. Shelter added another possible advantage: burrows, soil, tree cavities, freshwater environments, and protected sediments could reduce exposure to heat, fire, falling debris, or extreme temperature changes. But shelter only solved the first problem. An animal still had to emerge, find food, reproduce, and maintain a population after the immediate danger passed, which is why scientists avoid treating burrowing behavior as a complete explanation for survival. Freshwater environments are particularly interesting because some food webs there can rely heavily on organic material washed in from land or stored within sediments, and this may have made certain communities less immediately dependent on fresh photosynthesis than many open terrestrial or marine systems. Crocodilian relatives, turtles, amphibians, fish, birds, and mammals all show that survival crossed several very different branches of life, so there was no single winning body plan. Instead, The extinction appears to have favored combinations of traits that happen to remain useful under a world of darkness, cooling, damaged habitats, and reduced food. The distant mammalian lineages that would eventually contribute to primate ancestry belonged somewhere within this pattern, not because they possessed a hidden advantage designed for the future, but because some populations survived long enough to reproduce while many surrounding lineages did not. Their small size may have reduced absolute food requirements. Flexible feeding may have widened the range of usable resources, and sheltering behavior may have protected some individuals from immediate hazards. Yet each of these ideas must remain probabilistic rather than absolute. Because the fossil record does not allow us to reconstruct the exact behavior of every surviving species during the crisis, what it does show is that mammals as a broader group crossed the boundary and later diversified greatly. While many ecological roles once occupied by non-avian dinosaurs became vacant, this later expansion can make survival look inevitable when viewed backward from the existence of humans, but nothing about it was guaranteed. If different mammalian populations had disappeared, the later branches leading toward primates might never have existed, and if environmental recovery had taken another path, entirely different groups could have dominated the ecosystems that followed. Survival at the boundary therefore represents a narrow continuity through evolutionary time. A population needed enough food to remain alive, enough shelter to avoid lethal conditions, enough individuals to find mates, and enough reproductive success to produce another generation. Then those descendants had to repeat the process while ecosystems slowly reorganized around them. Strength mattered only when it could be supported by available energy. Specialization mattered only while the specialized resource remained. And dominance mattered only while the environmental system that made dominance possible continued to function. The extinction stripped away many of those supports, leaving survival dependent on ordinary traits that had evolved for older environments, but happened to remain useful under extraordinary conditions. The future of mammals, birds, reptiles, amphibians, fish, plants, and countless smaller organisms pass through this filter unevenly. And somewhere within those surviving populations lay the distant biological continuity from which humans would emerge tens of millions of years later, not because the catastrophe selected for humanity, but because some small bodies, flexible diets, and hidden places allowed enough life to remain when the larger Cretaceous world could no longer support what it had supported before. Survival across the Cretaceous-Paleogene boundary did not mean that the organisms which endured were more advanced, more intelligent, or somehow better designed than the species that disappeared. Because evolution does not arrange life on a ladder from inferior forms to superior ones, it produces populations adapted to particular environments, and when those environments change abruptly, the traits that once supported success can become liabilities, while ordinary traits in other organisms can suddenly become useful. Non-avian dinosaurs had occupied terrestrial ecosystems for an immense span of geological time. Many were highly successful in the environments that existed before the Chicxulub impact. Their disappearance, therefore, cannot be understood as evidence that they had reached an evolutionary dead end. Rather, the conditions supporting many of their populations were altered so quickly and so extensively that established ways of obtaining food, reproducing, and using habitat became increasingly difficult to maintain. Mammals were not waiting beneath them as a more advanced replacement. Many mammalian species also disappeared during the extinction, and the survivors represented only some branches of a much larger evolutionary diversity. The same pattern can be seen among birds, reptiles, amphibians, fish, plants, and marine organisms, where some lineages crossed the boundary while closely related groups did not. Survival was therefore selective without being purposeful. An organism could possess characteristics that happened to fit the new conditions, even though those characteristics had evolved long before the catastrophe for entirely different reasons. A small animal might require less total food than a giant herbivore. A seed-eating bird might have access to stored plant energy after fresh vegetation declined. A freshwater animal might occupy a food web partly supported by detritus, and a burrowing mammal might be buffered from some surface hazards. But none of these traits made those organisms universally superior. Place the same species in another environment or expose it to a different catastrophe, and the result could be reversed. This is one of the most important ideas for understanding the distant evolutionary road toward human beings. Because our existence can tempt us to read the past backward, and imagine that mammalian survival was a necessary step toward humanity. Yet the mammals living near the end of the Cretaceous had no special relationship to a future human world. They were simply animals trying to survive within their own ecological conditions. Some branches continued and others ended. And only much later did descendants of surviving mammals diversify into forms that included early primates. There was no hidden direction guiding that sequence. The extinction removed many existing possibilities while leaving others open, and chance interacted with biology at every stage. Geography mattered because populations living far from the most destructive physical effects could have different opportunities. Habitat mattered because freshwater, underground, coastal, forest, and open environments responded differently. Diet mattered because some food sources persisted longer than others. Reproduction mattered because populations had to replace losses. And body size mattered because energy requirements changed the amount of food needed for continued survival. None of these factors acted alone, which is why scientists are cautious about reducing the survival pattern to one simple rule. Even groups that seem broadly resilient suffered losses, and even successful traits could fail when local conditions became severe enough. The history that followed reinforces this point. Surviving mammals eventually expanded into many ecological roles, but birds also diversified. Crocodilians continued, turtles persisted, fish remained abundant, plants recovered, and marine communities rebuilt themselves from the lineages that crossed the boundary. The post-impact world was not the triumph of one supposedly superior form of life. It was a reconstruction assembled from survivors of many kinds, each carrying a different piece of evolutionary history forward. Some later became dominant in particular environments, while others remained relatively unchanged in broad body plan for long periods. Dominance itself continued to shift as climates, continents, habitats, and competitors changed through time. The lineage leading eventually toward humans would pass through many more environmental transitions before anything recognizably human appeared. So the connection between Chicxulub and our existence should remain modest. The impact altered ecological opportunities and removed many competing lineages. But it did not cause humans directly, and it did not guarantee that primates would evolve. It merely changed the biological landscape inherited by surviving mammals. Survival at the extinction boundary was therefore not a medal awarded to the strongest organisms. It was the continuation of certain populations through a particular combination of physical destruction, darkness, cooling, food scarcity, habitat change, and ecological chance. And recognizing that removes the false idea that extinction separates winners from losers according to some universal biological ranking. What survived was what happened to remain viable under those extraordinary conditions, and from those uneven remnants the next living world slowly began. The lineages that crossed the Cretaceous-Paleogene boundary did not emerge from the catastrophe unchanged, but they carried enough biological continuity into the Paleogene for life to rebuild from what remained. Birds survived as the only dinosaur lineage to pass through the extinction and later diversified into many forms. Mammals also crossed the boundary despite suffering heavy losses, while turtles, crocodilian relatives, amphibians, fish, and many other groups continued in different proportions. The pattern was never one of simple victory, because survival at the boundary often meant that only a fraction of a once broader lineage remained. And those survivors entered landscapes and waters where food webs, habitats, competitors, and climate had been deeply altered. Some of the animals that persisted were able to use freshwater environments, detritus-based resources, seeds, insects, carrion, or other foods that could remain available even when fresh photosynthetic production was reduced. But no single resource or behavior explains every surviving group, and the fossil record shows that extinction intensity varied greatly among different branches of life. This matters because the world after Chicxulub was not a blank planet waiting to be filled. Forests did not vanish forever. Oceans did not become empty. And surviving communities continued functioning in simplified or reorganized forms. Plant recovery began from seeds, spores, roots, and surviving vegetation. Freshwater systems retained organisms capable of using stored organic material, and marine ecosystems eventually rebuilt around the plankton and animals that had crossed the boundary. Birds carried one branch of dinosaur evolution forward, meaning the age of dinosaurs did not end in the absolute sense often imagined. Non-avian dinosaurs disappeared, but their avian relatives continued and remained part of the modern world. Mammals, likewise, did not suddenly become dominant everywhere immediately after the impact. Their later expansion unfolded over much longer periods, as surviving populations diversified into ecological opportunities opened by extinction. This distinction is especially important for the distant origin of human beings, because the mammalian continuity that eventually allowed primates to evolve depended on lineages surviving the crisis. Yet those survivors were not early versions of us, and they were not selected because they would one day produce humans. They were animals adapted to their own environments, and the branches leading toward primates appeared much later within a constantly changing mammalian tree. The importance of their survival lies simply in continuity. If every relevant mammalian branch had ended at the boundary, the particular evolutionary path that eventually produced humans could not have continued in the same form. The impact did not create that path or guarantee its outcome. It removed enormous amounts of biological diversity and left a different collection of lineages to inhabit the future. The same was true for crocodilian relatives and turtles, whose survival shows that large-scale extinction did not erase all reptiles, and for amphibians and fish, many of which persisted because their ecological settings and food webs responded differently from exposed terrestrial systems. Even among these groups there were losses, so modern survivors should never be used as proof that an entire category passed through the catastrophe easily. Survival belonged to particular populations and lineages, not to simple labels. And after the boundary, those populations faced the long work of ecological recovery without any intention or direction. Generations reproduced, populations expanded or contracted, plants recolonized disturbed ground, predators encountered new combinations of prey, and communities slowly acquired structures different from those of the late Cretaceous. Some ecological roles that had once belonged to extinct organisms were eventually occupied by descendants of survivors, while other roles disappeared or changed entirely. This process did not restore the old world, it produced a new one from inherited fragments, and that is the deeper meaning of the lineages that carried life forward. They preserved pieces of evolutionary history through a bottleneck created by physical catastrophe and ecological collapse. Every living bird today represents the continuation of one dinosaur branch. Every modern mammal belongs to a broader history that crossed the same boundary, and our own species exists very far downstream from that survival. not as the purpose of the event, but as one contingent result among countless possible futures that were narrowed when so many other branches ended. The extinction therefore changed the composition of life, not only by removing species, but by deciding, through the interaction of environment, biology, and chance, which evolutionary histories remained available to continue. After the Cretaceous-Paleogene extinction removed many established species, the surviving world contained ecological opportunities that had not existed in the same form before, because when a lineage disappears, it leaves behind more than an empty space on the landscape. It also leaves feeding roles, nesting places, hunting strategies, patterns of movement, and access to resources that other organisms may eventually begin to use. Yet this did not happen instantly. The first Paleogene ecosystems were still recovering from severe disruption. Food webs had been simplified, plant communities were rebuilding, and surviving populations were often small or unevenly distributed. So the early world after the extinction was not a peaceful open field waiting for mammals and birds to expand. It was a damaged biological system in which survival remained difficult. As environments stabilized and primary production recovered, however, some populations began to increase and diversify, and over many generations descendants could move into ecological roles that had once been occupied by species that no longer existed. Mammals are a clear example, because several mammalian lineages survived the boundary and later expanded into a much wider range of body sizes, diets, and habitats. But this expansion should not be described as an immediate replacement of dinosaurs. Non-avian dinosaurs had disappeared, while birds, which are living dinosaurs, continued to diversify, and many mammalian changes unfolded over long spans of evolutionary time, rather than in the first days or years after the impact. The important shift was that the structure of competition had changed. A small mammal living before the extinction existed in ecosystems dominated by established dinosaur communities, while its distant descendants later encountered environments in which many large terrestrial roles had become vacant. This difference created opportunities, but opportunity alone does not determine what evolution will produce. Populations must survive, vary, reproduce, and adapt within changing environments, and many branches that appeared after the extinction would themselves later disappear. The same process occurred in plant communities, marine ecosystems, and among birds, reptiles, fish, and other survivors, because vacant ecological space is not a physical location that remains empty until one species arrives. It is a pattern of resources and relationships that can be reorganized in many possible ways. A feeding role once occupied by one herbivore may later be divided among several smaller species. A predator niche may change because the available prey has changed, and forests may recover with a different balance of plant species than before. This gradual rebuilding is important for understanding the distant beginning of human history, because the mammalian radiation that followed the extinction created evolutionary possibilities from which primates would later emerge. Yet there was no direct path from Chicxulub to humans. The impact did not produce primates, intelligence, upright walking, or any later human trait. It simply changed the ecological world inherent in the surviving mammals, and from that altered starting point, evolution continued through countless unrelated events. Climates shifted, continents moved, forests expanded and contracted, new species appeared, and old ones vanished. Only much later did primates become part of that history, which means the connection between the extinction and humanity is real but indirect. Our lineage exists within a mammalian tree whose deeper branches passed through the KPG crisis. But the form that tree eventually took was not predictable from the aftermath of the impact. This perspective also changes the meaning of extinction itself. When species disappear, the future does not simply lose a list of names. It loses entire sets of biological possibilities, behaviors, body plans, and ecological relationships that might otherwise have continued evolving. The survivors inherit not only more space, but also a narrower evolutionary world, and their descendants build the next ecosystems from what remains. After Chicxulub, that rebuilding eventually produced terrestrial communities very different from those of the late Cretaceous, with mammals becoming more varied and birds expanding into numerous ecological roles. But these changes were not signs that life had improved in some universal sense. They were signs that life had reorganized around a new set of survivors. The world did not recover by recreating what had been lost. It recovered by constructing new relationships from the lineages that remained. And this is why the extinction event matters so deeply to the history of life, because once ecological space opened, evolution continued forward from a reduced and altered foundation, carrying some ancient branches into the future while leaving many others permanently behind. Mammals that survived the Cretaceous-Paleogene extinction entered a world that was profoundly different from the one their ancestors had known, not because the planet had become empty, but because many of the ecological relationships that had shaped terrestrial life for millions of years had been removed or reorganized. Large non-avian dinosaurs were gone. Many plant and animal communities had been disrupted, and surviving populations had to function within landscapes still recovering from fire, reduced sunlight, climate disturbance, and the collapse of earlier food webs. The first mammals living beyond the extinction boundary were therefore not stepping immediately into abundance. They were surviving inside unstable ecosystems where food, shelter, and competition had changed over time as vegetation recovered and food webs became more productive again. Some mammalian lineages began to diversify into ecological roles that had previously been limited or occupied by other animals. Body sizes increased in some groups, diets became more varied, and populations spread through forests, open habitats, freshwater margins, and other environments. Yet this expansion occurred across many generations and should not be imagined as a sudden transformation in the immediate aftermath of the impact. Evolution required time for populations to accumulate differences and for ecological communities to rebuild, and the mammals that eventually occupied larger roles were descendants of survivors rather than the same individuals that had endured the catastrophe. This distinction matters because the extinction did not directly create new mammalian forms. It changed the conditions under which later evolution operated. The removal of many established competitors and predators altered which resources were available and which biological strategies could succeed, but surviving mammals still faced competition from birds, reptiles, other mammals, and changing environments. No ecological role remained permanently reserved for one lineage, and many mammalian branches that appeared during the Paleogene later disappeared themselves. The distant origin of primates belongs within this long period of reorganization, not within the first days after Chicxulub. The earliest members of the broader evolutionary history associated with primates emerged only later, after mammalian communities had already been changing for a considerable span of geological time. And scientists continue to study exactly how early primate relatives were related and when particular branches separated. So it would be misleading to describe a single surviving Cretaceous mammal as the direct known ancestor of humans. What can be said more securely is that the mammalian lineages from which later placental groups developed survived across the extinction boundary, and that the ecological world available to their descendants was very different from the world before the impact. Forests recovering in the Paleogene created habitats in which small mammals could exploit insects, fruit, seeds, and other resources, while changes in vegetation and climate continued to reshape where populations could live. Much later, branches within this expanding mammalian diversity would produce primates, and much later, still one primate lineage would eventually lead toward humans, but each of those transitions depended on additional environmental changes, extinctions, migrations, and evolutionary innovations that Chicxulub itself did not determine. This is why the connection between the asteroid and humanity should be understood as historical contingency rather than direct causation. If the impact had not occurred, mammalian evolution might have followed a different path, but science cannot reconstruct with certainty what that alternative world would have produced. Non-avian dinosaurs might have continued occupying many terrestrial roles, mammalian diversity might have developed differently, and primates as we know them might or might not have appeared. Such possibilities remain counterfactual and cannot be treated as facts. What the fossil record does show is that mammalian diversity expanded in important ways after the extinction, and that later ecosystems increasingly contained forms unlike those common in the Cretaceous. This transformation demonstrates how mass extinction can change evolution without directing it. By removing lineages and altering ecological competition, it changes the set of possibilities available to survivors. But the outcomes still depend on variation, natural selection, chance, geography, and environmental history across enormous spans of time. The mammals that entered the Paleogene therefore inherited both opportunity and loss. They gained access to ecological space that had not previously been available in the same way, yet they inherited a biosphere reduced by the disappearance of countless species and entire evolutionary branches. Their later success cannot erase that loss, nor should it make the catastrophe appear beneficial, simply because one distant consequence eventually included the emergence of humans. From the perspective of evolution, there was no intended exchange in which dinosaurs disappeared so mammals could rise. There was only a severe extinction followed by survival, recovery, and diversification among the lineages that remained. And our own ancestry is one very late consequence of that altered world, separated from the day of impact by tens of millions of years of additional change. The connection between the Chicxulub extinction and the distant origins of human beings is real, but it is indirect, because the impact did not create humans, primates, or even the earliest mammals. It changed the ecological conditions under which surviving mammalian lineages continued to evolve. And that altered world became the starting point for everything that followed. After the extinction, many ecological roles once occupied by non-avian dinosaurs and other lost groups were no longer filled in the same way. Surviving mammals entered environments where competition, predation, vegetation, and available food had been reorganized. Over millions of years, some of those mammalian branches diversified into new forms, occupying forests, open habitats, trees, freshwater margins, and eventually many ecological niches that had not existed for them in the same way before, but none of this happened according to a plan. Evolution did not move steadily from small mammals toward primates and then toward humans. Instead, populations changed in response to local conditions. Some lineages expanded, some remained limited, and many disappeared. While climates shifted, continents moved, forests changed, mountains rose, oceans opened and closed, and new environmental pressures repeatedly altered the direction of natural selection. Primates appeared much later within this already diverse mammalian world, and even then there was no inevitable path toward humanity. Early primates diversified into different branches, adapted to different environments. Most of those branches did not lead toward humans, and the lineage that eventually produced apes and later hominins emerged only after many additional evolutionary transitions. This long distance in time matters because it prevents a common misunderstanding. Chicxulub should not be described as the event that made humans possible in any simple or purposeful sense. The impact changed which branches of life remained available to continue, but it did not determine what those branches would become, if different mammals had survived, or if later climates had developed differently, or if other extinction events and environmental changes had unfolded along another path. The biological world could have looked very different. Science cannot know exactly what that alternative future would have produced, and it would be speculation to claim that humans definitely would or would not have appeared without the extinction. What can be said with more confidence is that our lineage belongs to a mammalian history that passed through the KPG boundary, and therefore our existence is connected to organisms that survived a crisis tens of millions of years before anything recognizably human evolved. This is one of the deepest ways the extinction event relates to the beginning of our story, not as a direct cause, but as a filter that removed enormous amounts of evolutionary diversity while allowing a smaller set of lineages to carry biological history forward. Those survivors inherited a planet in which the old ecological order had been broken, and their descendants gradually constructed new ecosystems from the pieces that remained. Birds continued the dinosaur lineage, mammals diversified, plants rebuilt forests, marine communities reorganized, and new relationships between predators, prey, pollinators, seed dispersers, and vegetation emerged across long spans of time. Within that changing world, some mammals adapted increasingly to life in trees. Some developed different sensory abilities, feeding strategies, social behaviors, and body plans, and much later certain primate branches gave rise to apes, then hominins, and eventually to our own species. But each stage involved its own environmental history and cannot be traced back to the asteroid as if one event predetermined the entire sequence. The more accurate lesson is that human origins are embedded inside a much older history of survival, loss, and contingency. We exist because an unbroken chain of reproduction continued through countless generations, including generations that lived through the aftermath of one of the largest mass extinctions in Earth's recent geological past. Yet alongside that continuity lies an equally important absence. The branches that disappeared at the KPG boundary never returned. Their possible futures ended, and every ecosystem that developed afterward was shaped as much by those absences as by the organisms that survived. When we look backward from the present, it is easy to treat survival as the beginning of progress, but evolution has no memory of a destination. It simply continues through whatever populations remain capable of reproducing under changing conditions. The distant path toward humanity therefore began not with a moment of triumph after the asteroid, but with a damaged biosphere slowly reorganizing itself. And somewhere among the surviving mammals was the biological continuity that would eventually, after tens of millions of years of further change, become part of the ancestry of us. The difference between an impact and an extinction is the difference between a physical event and a biological process. And understanding that distinction is essential to answering what really happened at the end of the Cretaceous. The Chicxulub impact itself occurred extremely quickly. A large extraterrestrial body reached Earth at enormous speed, transferred its energy into rock, water, and atmosphere, excavated a crater, launched ejecta, generated intense seismic disturbance, displaced seawater, and began altering atmospheric conditions within minutes and hours. Yet the disappearance of roughly 3/4 of species cannot be placed confidently inside that same narrow interval, because extinction does not occur simply when many individuals die. It occurs when every surviving population belonging to a species eventually fails to continue, and those failures can happen through many different pathways. Some organisms near the impact region may have been killed almost immediately by heat, shock, falling material, flooding, or landscape destruction, while populations far from Yucatan could survive the first day with little direct contact with those effects, only to encounter reduced sunlight, cooling, food scarcity, habitat disruption, and collapsing ecological relationships later. This difference explains why the first 24 hours remain extraordinarily important, without needing to claim that the entire mass extinction was completed before one day had passed. The impact created the physical conditions that pushed ecosystems toward crisis, but biological consequences unfolded according to the vulnerability of different populations. Plants damaged by fire or darkness could persist for some time before failing to reproduce. Herbivores could continue feeding on remaining vegetation before supplies declined. Predators could survive while prey remained available. And marine animals could persist even as the productivity of plankton beneath their food webs weakened. Each delay separated the instant of collision from the eventual disappearance of a lineage, and the fossil record usually does not preserve enough temporal detail to identify the exact last day of every species. What it does preserve is a sharp boundary associated with impact evidence and a profound change in biodiversity, allowing scientists to connect Chicxulub strongly with the extinction while remaining cautious about the precise timing of every biological loss. This distinction reaches directly toward the distant origin of human beings, because the mammalian branches that eventually contributed to primate ancestry had to survive both stages. Surviving the physical event was only the beginning. Their populations also had to remain viable through the environmental disruption that followed, find enough food, avoid enough predators and hazards, reproduce successfully, and carry their lineages into later generations. A single animal hiding underground on the day of impact would contribute nothing to the distant future if its population disappeared soon afterward. Continuity required reproduction across time, which is why the history connecting Chicxulub to mammals, primates, and eventually humans is ultimately a history of populations rather than individual survivors. The same principle helps explain why mass extinctions are so different from ordinary disasters. An earthquake, flood, fire, or storm can kill enormous numbers of organisms while leaving surrounding ecosystems capable of recovery. But a mass extinction changes the composition of life across broad regions and removes entire evolutionary branches. After Chicxulub, the danger came from several systems failing together: atmosphere, climate, vegetation, marine productivity, habitats, and food webs were all affected to different degrees, and when those pressures persisted long enough, populations that had survived the initial catastrophe could still cross the threshold beyond which recovery was no longer possible. By separating impact from extinction, we also avoid turning the title into an absolute conclusion unsupported by evidence. The first day was not the complete extinction, but it may have been the decisive opening in which the physical future of countless species was changed before their biological disappearance had fully unfolded. Earth did not become silent after 24 hours. Many animals were still alive. Forests still existed in some regions. Oceans still contained complex communities, and surviving populations continued reproducing. Yet the environmental systems supporting the late Cretaceous world had been altered so deeply that the old ecological order could not simply return. What disappeared afterward was not only individual life, but entire branches of evolutionary history, while the lineages that endured entered a new biological landscape from which future ecosystems would develop, including the very distant mammalian history that would eventually contain us. Long after the heat faded, the waves settled, and ecosystems began rebuilding. The rocks preserved evidence that something extraordinary had happened at the end of the Cretaceous, and this geological record is one of the strongest reasons scientists can connect the Chicxulub impact with the mass extinction rather than relying on a dramatic story alone. Around the world, a thin layer marks the boundary between rocks of the Cretaceous and those of the Paleogene. And in many places, this boundary contains unusually high concentrations of iridium, an element that is relatively scarce in Earth's surface rocks, but more common in many meteorites. The discovery of this anomaly provided an important clue that extraterrestrial material had reached Earth at approximately the same time as the biological turnover, but iridium by itself was not enough to establish the entire explanation. Scientists therefore looked for additional evidence, and over time, several independent lines began pointing toward the same event. One of the most important was shocked quartz. Quartz crystals containing microscopic deformation features produced only under extremely high pressures, conditions far beyond those generated by ordinary erosion or sediment burial. Such grains were found in boundary deposits associated with the end of the Cretaceous, indicating that a powerful shock event had occurred. Small glassy spherules and other droplets formed from molten material provided another clue. Because rock heated and ejected during a major impact can cool into tiny, rounded particles as it travels through the atmosphere. Deposits containing these materials have been identified in regions surrounding the Gulf of Mexico and at more distant locations, showing that material from the event was distributed far beyond the crater itself. Eventually, geophysical surveys revealed a vast, buried circular structure beneath the Yucatan Peninsula and the adjacent seafloor. And the Chicxulub crater became the physical source capable of explaining the worldwide impact signals. Drilling into the structure later recovered rocks that had been fractured, melted, shocked, and displaced under extreme conditions, including material associated with the crater's peak ring, allowing scientists to study directly how the crust responded to the collision. Age measurements from impact-related rocks and the geological position of the crater match the end Cretaceous boundary closely enough to support a causal connection with the extinction. Although no dating method can reconstruct every minute or day of an event 66 million years in the past. The strength of the evidence comes from convergence, not from one perfect sample. Iridium, shocked minerals, ejecta deposits, crater structure, sediment disturbance, fossil turnover, and numerical models all fit a coherent physical sequence. And each line of evidence can be tested separately. The rocks also help show why the extinction must not be described as 75% of species dying in exactly 24 hours. Geological layers can identify a relatively sharp interval in deep time, but they rarely preserve resolution fine enough to tell us whether the final population of every species disappeared within hours, days, months, or longer. What they demonstrate more securely is that the impact occurred at essentially the same geological boundary as an abrupt and profound biological change. This distinction matters to the distant history of human origins, because the evidence does not tell us that the asteroid was somehow directed toward producing mammals or primates. It tells us only that a physical event changed the biological conditions inherited by surviving lineages. The mammals whose descendants would eventually contribute to primate ancestry crossed a boundary that is now recorded as chemistry, minerals, fossil disappearance, and disrupted sediments. Their individual experiences are lost, and science should not invent them. But their continuity can be inferred from the fact that mammalian lineages persisted into the Paleogene and diversified afterward, while many other branches ended. The rocks, therefore, give us something more reliable than an imagined scene of the final day. They give us a material record of cause and consequence, preserved beneath younger landscapes long after the organisms involved were gone. And when those separate traces are read together, they show that the end Cretaceous catastrophe was not a legend built around one crater, but a planetary event written into the physical structure of Earth itself. The world that followed the Cretaceous-Paleogene extinction was not a better world, and it was not a world that had been cleared for humans. It was simply a different world built from the lineages that remained after an immense loss of biological diversity. Forests returned, oceans recovered, birds continued the dinosaur lineage, mammals diversified, and new ecological relationships formed where older ones had disappeared. But none of this restored what had been lost. Every extinct species represented a branch of evolutionary history that could no longer produce descendants, and many of those branches had existed for millions of years before ending near the same geological boundary. This is why the extinction should not be interpreted only as the event that opened ecological opportunities for mammals, because opportunity came through loss, and the later appearance of primates and humans does not transform that loss into a necessary or beneficial step. Our own lineage exists because mammalian populations happened to survive a crisis that eliminated many other possibilities, yet there was no rule saying that those survivors would eventually become anything resembling us. After the impact, they still had to pass through tens of millions of years of changing climates, shifting continents, evolving forests, new predators, new competitors, additional extinctions, and countless local environmental changes before the branches associated with primates appeared. Much later still, certain primate populations would enter evolutionary paths that eventually produced hominins, and only near the very end of this enormous sequence would members of our own genus emerge. The distance between Chicxulub and humanity is therefore so large that the impact should be understood as one alteration of the conditions of history rather than the direct beginning of the human story. But it remains deeply connected to us because our biological ancestry could continue only through an unbroken chain of populations that survived each generation between that ancient catastrophe and the present. Somewhere among the mammals living after the extinction were lineages whose distant descendants would eventually contribute to primate ancestry, and their survival reminds us that evolution depends not on strength in an absolute sense, but on whether populations remain capable of living and reproducing under whatever conditions happen to exist. A species can dominate an ecosystem for millions of years and still disappear when the environment moves beyond the limits that supported it. While a small and relatively inconspicuous lineage can continue simply because some of its ordinary traits remain useful during a particular crisis, this is not a story of progress. It is a story of contingency, and that distinction gives the extinction its educational value because life on Earth is both resilient and vulnerable. Resilient because ecosystems eventually recovered from an event that removed an extraordinary share of species. Vulnerable because recovery did not bring those extinct branches back. Once a lineage ended, its evolutionary future ended with it. The forests that later grew were not the same forests. The animals that later filled large ecological roles were not replacements in any literal sense, and the oceans that recovered were reorganized around the survivors that remained. The first 24 hours after Chicxulub were therefore not the moment when 75% of all life simply vanished. They were the opening of a planetary crisis in which shock, heat, water movement, ejecta, atmospheric change, darkness, cooling, reduced photosynthesis, habitat loss, and collapsing food webs began interacting across different timescales. Some organisms died almost immediately, others survived the first day and disappeared later, while a smaller set of lineages remained long enough to reproduce and carry biological history beyond the boundary. Understanding this difference makes the event more meaningful rather than less dramatic, because it shows that mass extinction is not merely a moment of destruction. It is a change in what futures remain possible. The rocks beneath Yucatan and the thin boundary preserved around the world tell us that a physical event lasting a very short time can alter evolutionary history for tens of millions of years. And our presence today is one distant consequence within that altered history, not its intended destination. The lesson is not that catastrophe was required for humanity to exist, but that every living species occupies a temporary position inside systems much older and larger than itself, systems dependent on atmosphere, climate, sunlight, oceans, plants, microorganisms, and relationships that can appear stable until several foundations are disturbed together. The Cretaceous world had endured for an immense span of time before those foundations changed, and when they did, survival was determined neither by dominance nor by destiny, but by the fragile continuity of populations through an unfamiliar environment. We inherited a planet shaped partly by that survival and partly by everything that was permanently lost. And if one brief event could remove so many evolutionary possibilities while leaving others to shape the distant future, how many different worlds might Earth have produced if that single day had unfolded another way?